Have you ever looked up at the night sky and wondered about the true scale of the cosmic structure we call home? The Milky Way stretches across the darkness like a river of stars, but what you're seeing represents just a fraction of its true mass. Tonight, we're embarking on a journey to answer one of the most profound questions in astronomy. How massive is the Milky Way? And I mean truly, incomprehensibly massive. We're talking about a galaxy so enormous that it contains hundreds of billions of stars, yet stars make up only a tiny fraction of its total mass. We're diving into a cosmic structure where the visible matter we can see represents less than 1/6 of what's actually there. A galactic giant where dark matter, that mysterious invisible substance, outweighs everything we can observe by a factor of 5 to 1. If you've ever felt insignificant looking up at the stars, just wait until you grasp the true scale of the galaxy those stars inhabit. Before we embark on this cosmic journey, I'd love to know where you're joining me from tonight. Drop your location in the comments below. There's something beautifully humbling about contemplating the Milky Way's immensity while scattered across our tiny corner of this vast galactic disk. Understanding 1 trillion suns. Now, I want you to imagine something for a moment. Picture our sun, that massive ball of nuclear fire that provides all the energy for life on Earth. Got that image in your mind? Good. Now imagine you could somehow gather up 1 trillion suns, each one identical to ours. The combined mass of all those stars would roughly equal the total mass of the Milky Way galaxy. That's right, 1 trillion solar masses. But here's what makes this even more mind-blowing. Despite containing the mass equivalent of 1 trillion suns, only about 60 billion actual stars exist in our galaxy. So where's all that extra mass hiding? The answer leads us into one of the greatest mysteries in modern astronomy. This isn't just another exploration where we rattle off some numbers and call it a day. We're going to explore how the Milky Way's massive scale has shaped the evolution of billions of stellar systems, influenced the formation of heavy elements that make up planets and life itself, and continues to act as a cosmic crucible where new stars are born every year. We're going to dive into recent discoveries that suggest the Milky Way is even more massive than we previously thought. With a dark matter halo that extends far beyond the visible disk and exerts gravitational influence across millions of light years. By the end of this journey, you'll understand why the Milky Way isn't just our home galaxy. It's a cosmic structure so massive that it warps space and time itself, bends the fabric of the universe around it, and dominates the gravitational landscape across a region of space larger than most galaxy groups. It's a world unto itself, containing more matter than most galaxies in the observable universe. And it's been growing for over 13 billion years through continuous cannibalization of smaller galaxies, the foundation of galactic scale. But let's start with the basics, because even the basics about the Milky Way are absolutely mind-blowing. When we talk about the Milky Way's mass, we're not just talking about something that's a bit bigger than a star cluster. We're talking about a scale so vast that it breaks our normal understanding of what a gravitational system should be. The Milky Way's diameter stretches across approximately 100,000 to 200,000 light-years, depending on where you measure the edge. To put that in perspective, light traveling at 186,000 miles per second takes 100,000 years to cross from one side of the galactic disk to the other. If you wanted to drive across the Milky Way at highway speeds, it would take you about 600 trillion years. That's longer than the current age of the universe by a factor of 50,000. But here's where it gets really interesting. The Milky Way isn't a flat disk like you might imagine when you see artistic representations. It's actually a complex three-dimensional structure with multiple components, each contributing to the galaxy's total mass in different ways. We're talking about a central bulge, a thin disk, a thick disk, spiral arms, a stellar halo, and that enormous dark matter halo that extends far beyond anything we can see. Think about that for a moment. This is a structure so large that light from stars on one side of the galaxy hasn't had time to reach stars on the other side since before humans evolved on Earth. And that distance exists not in empty space, but in a region packed with stars, gas clouds, dust, and that mysterious dark matter that dominates the galaxy's gravitational field. Now, if the Milky Way's diameter is 100,000 light-years across, you might think you could calculate its volume using simple geometry. But that's not how galactic structures work. The Milky Way isn't a sphere or even a simple disk. It's a complex spiral structure with density gradients, warped edges, and a thick halo that extends far beyond the visible disk. When astronomers calculate the Milky Way's volume, they're really defining a region of space where the galaxy's gravitational influence dominates over the expansion of the universe itself. This means the Milky Way's volume isn't just about how much space it occupies, it's about how much space it controls through gravity. And that gravitational influence extends across distances measured in millions of light-years, far beyond the visible edge of the galactic disk. The mass mystery revealed. The Milky Way weighs in at approximately 1 trillion solar masses. But here's the kicker. If you took all the stars we can actually see in the Milky Way and added them up, you'd only account for about 60 billion solar masses. Add in all the gas, dust, planets, black holes, neutron stars, and every other form of normal matter we can detect, and you might reach 100 to 200 billion solar masses. That's still only 10 to 20% of the galaxy's total mass. Let me repeat that. The Milky Way contains 6 to 10 times more mass in invisible dark matter than in all the stars, planets, and gas clouds combined. This incredible mass concentration exists in a form we cannot see, cannot touch, and barely understand. We know it's there only because of its gravitational effects on the visible matter we can observe. This invisible dark matter began to accumulate during the early formation of our galaxy over 13 billion years ago, when the universe was just a few 100 million years old. Back then, the cosmos was filled with vast clouds of dark matter that began collapsing under their own gravity, creating gravitational wells that attracted normal matter. The Milky Way began as one of these dark matter concentrations, gradually accumulating hydrogen and helium gas that eventually formed the first generation of stars. But the Milky Way didn't grow smoothly or peacefully. This massive galaxy built itself through violence and cannibalism, consuming dozens of smaller galaxies over billions of years. Each merger added new stars, new gas, and new dark matter to the growing cosmic structure. Some of these ancient collisions can still be detected today in the motions of stars that orbit the galaxy in unusual directions, marking them as immigrants from long-dead satellite galaxies. Galactic cannibalism today. This process of galactic cannibalism continues today. Right now, as you listen to these words, the Milky Way is in the process of tearing apart and consuming several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being stretched into a stream of stars that wraps around our galaxy like a ribbon. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are slowly being drawn into the Milky Way's gravitational embrace. In a few billion years, they too will be consumed, adding their mass to our already enormous galaxy. Computer simulations suggest that the Magellanic Clouds will collide with the Milky Way in approximately 2 to 3 billion years, adding their mass to our already enormous galaxy. This merger will trigger massive bursts of star formation as gas clouds collide and compress, potentially creating spectacular displays of stellar birth visible across the galaxy. The merger might also disturb the central supermassive black hole, possibly triggering a period of active galactic nucleus activity that would make the galactic center shine much brighter than it does today. Gravitational effects and orbital dynamics. But the Milky Way's mass isn't just impressive as a number on a page. It has real, tangible effects that we can observe and measure. The galaxy's gravity is so strong that it holds together a structure containing hundreds of billions of stars, each moving at hundreds of kilometers per second, yet maintaining coherent orbital patterns that have persisted for billions of years. The Sun itself orbits the center of the Milky Way at a speed of about 220 kilometers per second, That's nearly 500,000 miles per hour. At that incredible velocity, it still takes our solar system approximately 225 million years to complete one orbit around the galactic center. We call this time period a cosmic year. Since Earth formed 4.6 billion years ago, our solar system has completed only about 20 orbits around the galaxy. Think about what that means. The last time our solar system was in its current position relative to the galactic center, dinosaurs ruled the Earth. The time before that, the first reptiles were just beginning to evolve. And the time before that, complex life was just emerging from the oceans. The Milky Way's rotation operates on timescales so vast that entire epochs of Earth's history pass between cosmic landmarks. The cosmic ecosystem. The Milky Way's gravitational influence extends far beyond just holding stars in orbit. It acts like a cosmic ecosystem, regulating the formation of new stars, recycling heavy elements through stellar death and rebirth, and creating the chemical complexity necessary for planets and life to form. When massive stars explode as supernovae, they scatter heavy elements like carbon, oxygen, iron, and gold into space. These elements eventually incorporate into new generations of stars and planets. Every atom in your body, heavier than hydrogen, was forged in stars that lived and died within the gravitational embrace of the Milky Way. The galaxy's rotation creates spectacular spiral arms where gas and dust pile up, triggering waves of star formation. These spiral arms aren't fixed structures like the arms of a spinning wheel. Instead, they're density waves, regions where stars and gas temporarily slow down, creating traffic jams that compress gas clouds until they collapse to form new stars. Our solar system passes through these spiral arms periodically as it orbits the galaxy, potentially influencing Earth's climate and the rate of cosmic ray bombardment over geological timescales. The empty vastness. But here's something that might surprise you. Despite the Milky Way's enormous mass, most of the galaxy is actually empty space. If you could somehow stand on a planet orbiting a star near the galactic center, where stars are packed most densely, your nearest stellar neighbor would still be several light-years away. Even in the densest regions of our galaxy, stars are separated by distances millions of times larger than their own diameters. This emptiness reveals something crucial about the Milky Way's structure. It's not a solid object, but rather a gravitationally bound system of discrete particles, stars, gas clouds, and dark matter, all moving in complex orbital patterns around a common center. The cohesion of this system depends entirely on gravity, that weakest of the fundamental forces, operating across distances so vast that light takes thousands of years to traverse them, warping space and time. The Milky Way's mass creates a gravitational field so strong that it affects the very fabric of space and time itself. According to Einstein's theory of general relativity, mass curves space-time, and the more mass you have, the more pronounced that curvature becomes. The Milky Way's trillion solar masses create a gravitational well so deep that it significantly affects the trajectory of light passing through or near the galaxy. This gravitational lensing effect allows astronomers to detect the Milky Way's mass by observing how it bends light from more distant objects. When light from distant galaxies passes near our galaxy, the Milky Way's gravity acts like a cosmic magnifying glass, bending and distorting that light in predictable ways. By measuring these distortions, scientists can map the distribution of mass in the Milky Way, including the invisible dark matter that dominates the galaxy's gravitational field. The sphere of influence. But the Milky Way's gravitational influence extends even further than light-bending effects. The galaxy's mass creates what astronomers call a sphere of gravitational influence, a region of space where the Milky Way's gravity dominates over the general expansion of the universe. This sphere extends for approximately 3 million light-years in all directions, encompassing not just our galaxy, but also its satellite galaxies and neighboring galaxies like Andromeda. Within this vast region, the Milky Way's gravity determines the fate of smaller galaxies, gas clouds, and even the cosmic web of dark matter that connects galaxy clusters throughout the universe. Objects within the Milky Way's gravitational sphere are bound to our galaxy, meaning they will eventually merge with it or remain in orbit around it rather than being carried away by cosmic expansion. The central black hole and galactic bulge. The internal structure of the Milky Way is as complex as its size, and mass are impressive. At the very center of our galaxy lies Sagittarius A*, a supermassive black hole with a mass approximately 4 million times that of the Sunday. This might sound enormous, and it is by stellar standards, but it represents only a tiny fraction of the galaxy's total mass. The supermassive black hole contains about 0.00004% of the Milky Way's total mass. Yet, its gravitational influence shapes the orbits of stars in the central light year of the galaxy. Stars near Sagittarius A* move at incredible velocities, some reaching speeds of several percent of the speed of light as they whip around the black hole in highly elliptical orbits. These orbital motions provided the first direct evidence for the black hole's existence and allowed astronomers to calculate its mass with remarkable precision. Surrounding the central black hole is the galactic bulge, a roughly spherical collection of old stars that extends for thousands of light years around the galactic center. This bulge contains approximately 20 billion solar masses of stars, most of them red giants, and other old stellar populations that formed during the early history of the galaxy. The galactic disk structure. Beyond the bulge lies the galactic disk, a flattened structure about 100,000 light-years across, but only about 1,000 light-years thick. This is where most of the galaxy's visible mass resides, including our Sun and most of the stars you see when you look up at the night sky. The disk contains approximately 40 to 60 billion solar masses of stars, along with vast quantities of gas and dust that will eventually form new generations of stars. The disk itself isn't uniform, but instead exhibits a spectacular spiral structure with bright arms of young blue stars and red nebulae marking regions of active star formation. These spiral arms contain enhanced concentrations of gas and dust, compressed by density waves that travel around the galaxy like ripples on a pond. The spiral structure helps organize star formation on galactic scales, creating the stunning patterns we see when we observe spiral galaxies from the outside. Our solar system resides about 26,000 light-years from the galactic center, roughly halfway out to the visible edge of the disk. We orbit within what astronomers call the Orion Arm, a minor spiral feature located between two of the major spiral arms. This location provides us with a relatively stable environment, far enough from the galactic center to avoid the intense radiation and frequent stellar encounters near the core, but close enough to benefit from the steady supply of heavy elements produced by previous generations of stars. The dual disk system. But the disk we can see represents only part of the story. Recent observations have revealed that the Milky Way actually has two distinct disk components: a thin disk where most young stars reside, and a thick disk containing older stellar populations. The thick disk extends several thousand light-years above and below the galactic plane and contains stars with different chemical compositions than those in the thin disk, suggesting it formed earlier in the galaxy's history, possibly through the merger of smaller galaxies. Surrounding both disk components is the stellar halo, a roughly spherical distribution of old stars and globular clusters that extends far beyond the visible disk. This halo contains only a small fraction of the galaxy's stellar mass, perhaps 1% or less, but it provides crucial information about the Milky Way's formation history. Many halo stars orbit the galaxy in retrograde directions or on highly elliptical paths, indicating they originated in smaller galaxies that were captured and disrupted by the Milky Way's gravity billions of years ago. These stellar fossils preserve evidence of ancient galactic collisions that helped build the massive structure we inhabit today. The stellar halo also contains globular clusters, ancient spherical collections of hundreds of thousands to millions of stars packed into regions just tens of light-years across. The Milky Way hosts approximately 150 to 200 of these globular clusters, some of which are nearly as old as the universe itself, formed when the galaxy was just beginning to take shape over 13 billion years ago. These ancient stellar cities orbit the galactic center on vast looping trajectories that carry them far above and below the galactic plane, providing astronomers with laboratories to study stellar evolution and galactic dynamics across cosmic time. The dark matter halo dominates. But all these visible components, the bulge, the disks, the halo, the globular clusters, and every star you can see, together account for less than 20% of the Milky Way's total mass. The remaining 80% or more consists of dark matter, an invisible substance that reveals its presence only through gravitational effects. This dark matter forms an enormous halo that extends far beyond the visible galaxy, possibly reaching out 500,000 light-years or more from the galactic center. Within this vast dark matter halo, the visible Milky Way floats like a luminous island in an invisible ocean. The dark matter halo's shape remains uncertain, but most models suggest it's roughly spherical or slightly flattened, more extended than the visible disk, but less flattened than the stellar distribution. This dark matter structure provides the gravitational scaffolding that holds the entire galaxy together and determines the orbital velocities of stars throughout the galactic disk. Without dark matter's gravitational influence, the Milky Way as we know it could not exist. The visible matter alone lacks sufficient mass to hold the galaxy together at its observed rotation speeds. Stars in the outer regions of the galactic disk move so fast that they should fly off into intergalactic space, yet they remain bound to the galaxy because they're embedded in the dark matter halo's gravitational field. The rotation curve anomaly. This discovery emerged from observations of galactic rotation curves, measurements of how fast stars and gas clouds orbit at different distances from the galactic center. According to Newtonian physics, objects farther from the center of mass should orbit more slowly, just as outer planets in our solar system take longer to complete their orbits than inner planets. But when astronomers measured the rotation speeds of stars and gas clouds in the Milky Way and other spiral galaxies, they found something unexpected. Instead of decreasing with distance, the orbital velocities remained roughly constant far beyond the visible edge of the galactic disk. This flat rotation curve indicated the presence of additional mass, invisible mass, that extends far beyond the luminous matter we can see. The only explanation that fits the observations is a massive halo of dark matter surrounding the visible galaxy, providing the extra gravitational pull needed to keep stars in their observed orbits. Multiple independent lines of evidence now confirm dark matter's existence, from gravitational lensing observations to measurements of the cosmic microwave background radiation left over from the Big Bang. The nature of dark matter. Yet, despite decades of research, the fundamental nature of dark matter remains one of the biggest unsolved mysteries in physics. We know dark matter doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation in any detectable way. It passes through normal matter with barely any interaction, making it extraordinarily difficult to detect directly. Scientists have proposed numerous candidates for what dark matter might be. The leading hypothesis suggests dark matter consists of weakly interacting massive particles, hypothetical particles that have mass and gravitational influence, but interact only through gravity and possibly the weak nuclear force. Alternatively, dark matter might consist of axions, hypothetical particles predicted by certain extensions of particle physics theory, or perhaps primordial black holes formed in the early universe. Or it could be something entirely different, a new type of particle or field we haven't yet imagined. Experiments around the world are searching for direct evidence of dark matter particles. Deep underground laboratories shield sensitive detectors from cosmic ray interference, watching for the rare occasions when a dark matter particle might collide with an atomic nucleus. So far, no conclusive detections have been made, but the search continues with ever more sensitive instruments. Dark matter's galactic role. Whatever dark matter's fundamental nature, its role in galactic dynamics is clear and measurable. The Milky Way's dark matter halo acts like a cosmic stabilizer, maintaining the galaxy's structure over billions of years despite the chaotic motions of hundreds of billions of stars. Computer simulations of galaxy formation consistently show that without dark matter, spiral galaxies like the Milky Way cannot form. The dark matter provides the gravitational seeds around which normal matter accumulates, forming the first stars and eventually building up the complex galactic structures we observe today. The distribution of dark matter throughout the Milky Way likely follows a roughly spherical pattern, densest near the galactic center and gradually decreasing with distance. However, the exact density profile remains uncertain, with different models predicting slightly different distributions. Some evidence suggests dark matter might be clumpier than originally thought, with substructure consisting of smaller dark matter concentrations orbiting within the larger halo. These dark matter subhalos might host dwarf galaxies or remain completely dark, visible only through their gravitational effects on nearby stars and gas. Measuring the invisible. How do astronomers measure something they cannot see? The techniques for determining the Milky Way's mass and the distribution of its dark matter component are ingenious and rely on carefully observing the motions of objects we can see. One primary method involves tracking the velocities of stars and gas clouds at various distances from the galactic center. By measuring how fast these objects orbit and applying Newton's laws of gravity, astronomers can calculate the total mass contained within each orbital radius. These measurements revealed the existence of dark matter when they showed far more mass than could be accounted for by visible stars and gas. Another technique uses stellar streams, long ribbons of stars created when small galaxies, or globular clusters, are torn apart by the Milky Way's tidal forces. The shapes and motions of these streams depend on the total mass distribution of the galaxy, including the dark matter halo. By modeling how these streams move and evolve over time, researchers can constrain the Milky Way's total mass and the shape of its dark matter halo. Satellite galaxies also serve as tracers of the Milky Way's gravitational field. The small and large Magellanic Clouds, along with dozens of smaller dwarf galaxies, orbit the Milky Way at various distances. Their orbital velocities and trajectories provide information about the galaxy's total mass and how that mass is distributed in 3 dimensions. The Gaia Revolution. Recent years have witnessed a revolution in our understanding of the Milky Way's structure and dynamics, driven largely by data from the Gaia Space Telescope. Launched by the European Space Agency, Gaia has measured the positions, distances, and motions of more than 1 billion stars throughout the galaxy with unprecedented precision. This wealth of data allows astronomers to map the Milky Way's structure in 3 dimensions and trace the motions of stars with extraordinary accuracy. These measurements have revealed subtle features in the galaxy's structure, including ripples and waves in the galactic disk that may result from ancient collisions with smaller galaxies. Gaia's data has also improved estimates of the Milky Way's total mass. By tracking the motions of distant globular clusters and satellite galaxies, researchers used Gaia measurements to calculate that the Milky Way contains approximately 1.5 trillion solar masses within a radius of about 130,000 light-years from the galactic center. This represents a significant increase from earlier estimates and suggests the Milky Way might be even more massive than its neighbor, the Andromeda Galaxy, which was previously thought to be the larger of the 2 galaxies in our local group. Mass distribution across the galaxy. The Milky Way's mass isn't distributed uniformly. Instead, it concentrates more heavily toward the galactic center, then gradually decreases with distance, though never dropping to 0 thanks to the extended dark matter halo. At the very center, the supermassive black hole Sagittarius A** dominates the innermost light year with its 4 million solar mass concentration. Surrounding it, the galactic bulge contains approximately 20 billion solar masses, packed into a region several thousand light-years across. The galactic disk, extending out to roughly 50,000 light-years from the center, contains perhaps 60 billion solar masses of stars, plus another 10 to 20 billion solar masses of gas and dust. But even within this relatively small radius, dark matter outweighs visible matter by a factor of at least 3 to 1. Beyond the visible disk, the stellar mass drops dramatically, but the dark matter continues to dominate. Out to distances of 100,000 light-years, the dark matter halo may contain 500 billion solar masses or more. And the halo doesn't stop there. It continues extending outward, gradually thinning but never completely disappearing, perhaps reaching out as far as 500,000 to 1 million light-years from the galactic center. The local group context. To truly appreciate the Milky Way's mass, we need to consider it in the context of its cosmic neighborhood. Our galaxy doesn't exist in isolation, but instead belongs to a collection of galaxies called the local group, a gravitationally bound structure containing more than 50 galaxies, spanning a region approximately 10 million light-years across. The local group contains 3 large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Of these 3, the Milky Way and Andromeda dominate, each containing roughly 1 trillion solar masses, while Triangulum weighs in at only about 50 billion solar masses, making it substantially less massive than its larger neighbors. Surrounding these massive galaxies are dozens of dwarf galaxies, small systems containing anywhere from a few million to a few billion stars. Many of these dwarfs orbit the Milky Way or Andromeda as satellite galaxies, caught in the gravitational embrace of their larger neighbors. The large and small Magellanic Clouds represent the Milky Way's most prominent satellites, visible to the naked eye from the southern hemisphere as fuzzy patches of light. The large Magellanic Cloud contains approximately 10 billion solar masses, while the small Magellanic Cloud holds about 7 billion solar masses. Together, they represent substantial additions to the Milky Way's total gravitational system. The dance with Andromeda. The Milky Way and Andromeda galaxies are not just neighbors. They're locked in a gravitational dance that will eventually lead to a dramatic collision and merger. Despite being separated by approximately 2.5 million light-years, these 2 massive galaxies are moving toward each other at a speed of about 110 kilometers per second. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide in one of the most spectacular events in galactic evolution. This won't be a collision in the traditional sense. Galaxies are mostly empty space, so actual stellar collisions will be extremely rare. Instead, the 2 galaxies will pass through each other, their gravitational fields interacting in complex ways that will dramatically reshape both systems. The merger will trigger massive bursts of star formation as gas clouds from both galaxies collide and compress. The night sky, viewed from Earth, if our planet still exists and remains habitable, will be transformed as the 2 galaxies' stellar populations mix and mingle. The combined system will eventually settle into a single giant elliptical galaxy, sometimes whimsically called Milkomeda, containing roughly 2 trillion solar masses. This future merger highlights an important point about galactic mass. The Milky Way's current mass of 1 trillion solar masses represents only a snapshot in time. Galaxies are dynamic systems that grow through mergers and accretion and shrink through processes like tidal stripping. The Milky Way was less massive in the past and will be more massive in the future as it continues to accumulate smaller galaxies and eventually merges with Andromeda. Star formation and chemical evolution. The Milky Way's enormous mass plays a crucial role in the ongoing process of star formation and chemical evolution. The galaxy contains approximately 10 billion solar masses of cold gas, mostly hydrogen and helium, available to form new stars. This gas resides primarily in the galactic disk, concentrated in molecular clouds that can contain millions of solar masses of material. Star formation occurs when regions of these clouds become dense enough to collapse under their own gravity. The Milky Way currently forms new stars at a rate of approximately 1 to 3 solar masses per year. This might not sound like much compared to the galaxy's total mass, but over billions of years, it represents the creation of billions of new stars. Each generation of stars enriches the interstellar medium with heavy elements. Massive stars live fast and die young, exploding as supernovae after just a few million years, and scattering elements like carbon, oxygen, iron, silicon, and gold into space. These elements mix with the existing gas, eventually incorporating into new stars and planetary systems. The Sun is a product of this cosmic recycling. Its chemical composition reflects billions of years of stellar evolution within the Milky Way. Every element heavier than hydrogen and helium in your body, in Earth's rocks, in the water you drink, was created inside stars that lived and died within our galaxy. The Milky Way's mass provides the gravitational reservoir needed to retain this enriched gas. Smaller galaxies with less mass have weaker gravitational fields and can lose significant amounts of their gas through supernova-driven winds. But the Milky Way's trillion solar mass bulk anchors its gas supply, ensuring continued star formation and chemical enrichment for billions of years to come. The metallicity gradient. This chemical enrichment doesn't occur uniformly throughout the galaxy. Instead, there's a metallicity gradient, with stars near the galactic center generally containing higher abundances of heavy elements than stars in the outer disk. This gradient exists because star formation has been more active in the inner galaxy, where gas densities are higher and stellar populations are more concentrated. More stars mean more supernovae, which means more heavy elements scattered into the interstellar medium. The inner galaxy has cycled through more generations of stellar birth and death, progressively enriching the gas from which new stars form. Our solar system, located in the galactic suburbs about 26,000 light-years from the center, has a metallicity that's roughly average for the Milky Way's disk. The Sun contains about 1.4% of its mass in elements heavier than helium, a composition that reflects the accumulated products of stellar evolution over the roughly 8 billion years between the galaxy's formation and the Sun's birth. The galaxy as a living system. All these processes, star formation, chemical enrichment, galactic rotation, and gravitational interactions, combine to make the Milky Way a living, evolving system. It's not a static structure frozen in time, but a dynamic entity constantly changing and growing. Gas falls into the galactic disk from the surrounding halo, feeding ongoing star formation. Small galaxies fall into the Milky Way, adding their mass and triggering bursts of stellar birth. Stars age and die, returning enriched material to the interstellar medium. New stars form, continuing the cycle of cosmic creation and destruction. The Milky Way's massive scale makes all this possible. Without sufficient mass to retain gas against supernova explosions and stellar winds, the galaxy would have exhausted its fuel for star formation billions of years ago. Without the dark matter halo's gravitational influence, the galactic disk would have dispersed, unable to maintain its coherent spiral structure. The Milky Way's trillion solar masses aren't just an impressive number. They represent the accumulated product of 13 billion years of cosmic evolution, from the earliest dark matter structures that formed in the infant universe, through countless episodes of galactic cannibalism and star formation, to the majestic spiral galaxy we inhabit today. The galactic center's extreme environment. Nowhere is the Milky Way's mass more concentrated than in the galactic center, a region of extreme conditions unlike anywhere else in the galaxy. Within the innermost few light-years, stars orbit at velocities reaching thousands of kilometers per second, their motions governed by the supermassive black hole's immense gravitational field. These central stars, catalogued as the stars, have provided some of the best evidence for the black hole's existence. Astronomers have tracked their orbits for decades, watching them whip around an invisible point in highly elliptical paths. One star, designated STU, has an orbital period of just 16 years and approaches within 17 light-hours of the black hole at its closest approach. At that distance, the star experiences extreme gravitational effects. Time dilation becomes measurable, with clocks on the star running slightly slower than clocks farther from the black hole. the star's light becomes gravitationally redshifted as it climbs out of the intense gravitational well. These relativistic effects, predicted by Einstein's general relativity, have been directly observed and measured, providing spectacular confirmation of our understanding of gravity in extreme environments. The galactic center also hosts intense star formation in the circumnuclear disk, a ring of dense molecular gas orbiting a few light-years from Sagittarius A*. Despite the black hole's disruptive influence and intense radiation environment, new stars continue to form in this region, including some of the most massive stars known in the galaxy. The central molecular zone. Surrounding the immediate galactic center lies the central molecular zone, a region extending several hundred light-years that contains approximately 10% of the Milky Way's total molecular gas mass. This represents an enormous concentration of star-forming fuel. Surrounding the immediate galactic center lies the central molecular zone, a region extending several hundred light-years that contains approximately 10% of the Milky Way's total molecular gas mass. This represents an enormous concentration of star-forming fuel. Yet surprisingly, the star formation rate in this region is lower than expected given the amount of available gas. This star formation suppression likely results from the extreme conditions near the galactic center. Powerful magnetic fields, intense radiation, strong gravitational shear forces, and turbulent gas motions all conspire to make star formation more difficult in this environment. The gas clouds experience such violent conditions that they're often torn apart before they can collapse to form new stars. When stars do manage to form in the central molecular zone, they often appear in dense clusters containing thousands to tens of thousands of stars, packed into regions just a few light-years across. These clusters experience intense internal dynamics, with close stellar encounters and even collisions occurring far more frequently than in the calmer regions of the galactic disk where our solar system resides. The central molecular zone also serves as a unique laboratory for studying molecular chemistry under extreme conditions. The intense radiation field, high temperatures, and extreme pressures create exotic molecules rarely found elsewhere in the galaxy. Astronomers have detected dozens of different molecular species in this region, from simple molecules like carbon monoxide to complex organic compounds containing 10 or more atoms. The energetic core. The mass concentration in the galactic center doesn't just create extreme gravitational effects. It also produces prodigious amounts of energy across the electromagnetic spectrum. While Sagittarius A* appears relatively quiet compared to the supermassive black holes in some other galaxies, it still emits significant radiation, particularly in radio wavelengths. Occasionally, the black hole flares dramatically when gas clouds or possibly even stars fall close to its event horizon. During these events, the infalling material heats to millions of degrees, radiating intense X-rays and gamma rays before disappearing forever beyond the point of no return. The galactic center region also hosts numerous other high-energy phenomena. Massive stars end their lives in spectacular supernova explosions, creating neutron stars and stellar mass black holes. These compact objects can form binary systems, spiraling together and eventually merging in cataclysmic events that release gravitational waves rippling through the fabric of space-time itself. In fact, observations of gravitational waves by detectors like LIGO and Virgo suggest that stellar mass black hole mergers occur throughout the galaxy, with the highest rates expected in dense stellar environments like the galactic center and globular clusters. Magnetic fields and cosmic rays. The Milky Way's mass and rotation generate another invisible but crucial component, a large-scale magnetic field that permeates the galactic disk and extends into the halo. This magnetic field, though incredibly weak by terrestrial standards with a strength of just a few microgauss, plays important roles in galactic dynamics and the evolution of the interstellar medium. The galactic magnetic field helps regulate star formation by providing support against gravitational collapse in gas clouds. It channels the flow of ionized gas in the interstellar medium and influences how supernova remnants expand and evolve. The field also serves as a cosmic particle accelerator, energizing charged particles to relativistic velocities. These energetic particles, called cosmic rays, constantly bombard the Milky Way. They consist primarily of protons and atomic nuclei, accelerated to speeds approaching the speed of light, carrying enormous kinetic energies. When cosmic rays strike atoms in the interstellar medium, they produce a cascade of secondary particles and radiation, contributing to the ionization of interstellar gas and influencing its chemistry. The origin of cosmic rays, particularly the highest energy particles, remains an active area of research. Supernova remnants are likely responsible for most galactic cosmic rays, with the shock waves from these explosions accelerating particles to tremendous energies. But the most energetic cosmic rays might originate from more exotic sources like supermassive black holes or the remnants of massive stellar collisions. The Milky Way's magnetic field traps these cosmic rays, preventing them from escaping immediately into intergalactic space. This creates a cosmic ray halo surrounding the galaxy, where particles bounce back and forth along magnetic field lines, gradually diffusing outward over millions of years. The Fermi Bubble's mystery. One of the most intriguing recent discoveries about the Milky Way's structure is the presence of enormous bubble-shaped structures extending above and below the galactic plane. These Fermi bubbles, named after the Fermi Gamma-ray space telescope that discovered them, stretch for approximately 25,000 light-years in each direction, reaching far above and below the galactic disk. The bubbles emit gamma rays, the highest energy form of electromagnetic radiation, suggesting they contain populations of extremely energetic particles. Their sharp edges and symmetrical structure indicate they resulted from a powerful energetic event originating at the galactic center, possibly a period of intense activity from Sagittarius A*, or perhaps a burst of star formation and supernovae in the central molecular zone. Whatever created the Fermi bubbles must have been extraordinarily powerful, pumping enough energy into the surrounding medium to create these vast structures visible across thousands of light-years. The bubbles may be between 6 and 9 million years old, relatively recent in galactic terms, suggesting that the Milky Way's galactic center was significantly more active in the recent past than it is today. These structures demonstrate that even a galaxy as massive as the Milky Way can experience dramatic changes over timescales of millions of years, with explosive events reshaping vast regions of the galactic halo. The stellar populations tell stories. The diversity of stellar populations throughout the Milky Way provides a fossil record of the galaxy's history. By studying the ages, chemical compositions, and orbital patterns of different stellar groups, astronomers can reconstruct how the galaxy formed and evolved over billions of years. The oldest stars in the Milky Way, found primarily in the stellar halo and globular clusters, date back more than 13 billion years, to when the universe was less than 1 billion years old. These ancient stars formed from primordial gas that contained almost no elements heavier than helium, because the first generations of stars hadn't yet had time to enrich the interstellar medium with heavy elements. These metal-poor stars have chemical compositions dramatically different from the Sunday. Some contain less than 1/10,000th the iron abundance of our solar system, marking them as relics from the galaxy's earliest epochs. Their existence and properties constrain models of how the first stars formed and how they influence subsequent generations. In contrast, the youngest stars in the galactic disk, found in regions of active star formation like the Orion Nebula, formed from gas that has been enriched through multiple cycles of stellar birth and death. These metal-rich stars have chemical compositions reflecting billions of years of nucleosynthesis, with abundances of heavy elements hundreds of times greater than the oldest stellar populations. Stellar archaeology reveals galactic history. Between these extremes lies a continuum of stellar ages and compositions that together tell the story of the Milky Way's chemical evolution. By studying large samples of stars and measuring their chemical fingerprints through spectroscopy, astronomers practice a kind of stellar archaeology, reconstructing the galaxy's past from the fossil record preserved in starlight. This research has revealed that the Milky Way's chemical evolution wasn't smooth and steady. Instead, it proceeded in fits and starts, with periods of intense star formation and chemical enrichment alternating with quieter epochs. Some of these bursts of activity coincide with major merger events, when smaller galaxies fell into the Milky Way and triggered waves of star formation through gravitational interactions. The Gaia mission has revolutionized this field by providing precise measurements of stellar positions and motions for over 1 billion stars. Combined with spectroscopic surveys that measure stellar chemical compositions, this data allows astronomers to identify distinct stellar populations and trace them back to their origins. Some groups of stars move together through the galaxy with similar velocities and chemical compositions, marking them as remnants of ancient star clusters or dwarf galaxies that have been torn apart by tidal forces. These stellar streams wind through the galaxy like ghostly rivers, preserving evidence of merger events that occurred billions of years ago. The Sagittarius Stream discovery. One of the most spectacular examples is the Sagittarius Stream, a vast ribbon of stars wrapping completely around the Milky Way. This stream represents the tidal debris of the Sagittarius dwarf elliptical galaxy, a small galaxy currently in the process of being consumed by the Milky Way's gravitational field. Computer simulations suggest the Sagittarius dwarf has made multiple passages through the Milky Way's disk, with each passage stripping away more of its stars. The stream extends for hundreds of thousands of light years, completely encircling our galaxy in multiple wraps like thread wound around a spool. The mass of the original Sagittarius dwarf galaxy before it began being disrupted might have been several billion solar masses, making it a significant contribution to the Milky Way's total mass. Most of that mass has now been stripped away and distributed throughout the galactic halo, with the remaining core containing perhaps only a few tens of millions of solar masses. This ongoing merger provides a real-time example of the galactic cannibalism that has built the Milky Way into the massive structure we see today. Similar processes have occurred dozens or hundreds of times throughout the galaxy's history, with each merger adding mass and leaving distinctive signatures in the stellar populations and dynamics. The Milky Way's assembly history. The complete assembly history of the Milky Way remains an active area of research, but a general picture has emerged. The galaxy began forming more than 13 billion years ago, when dark matter in a small region of the early universe began collapsing under its own gravity, creating a gravitational well that attracted normal matter. The first stars formed in small protogalactic fragments, mini-galaxies containing just millions or billions of solar masses. These fragments gradually merged together through gravitational attraction, building up larger and larger structures. The process was chaotic and violent, with collisions scrambling stellar orbits and triggering intense bursts of star formation. Over time, the Milky Way's inner regions settled into a rotating disk as angular momentum was redistributed through gravitational interactions. Gas falling toward the galactic center conserved angular momentum, forcing it into a flattened, rotating structure. Stars forming from this gas inherited the disk's rotation, creating the ordered orbital patterns we see today. But not all mergers produced disk stars. Major collisions with galaxies containing comparable masses could heat the disk, puffing it up into a thicker structure or even disrupting it entirely. The thick disk population and the stellar halo likely formed during these violent epochs, when the young Milky Way was still assembling from smaller fragments. Approximately 10 to 11 billion years ago, the Milky Way experienced what might have been its last major merger with a galaxy of comparable size. This event, sometimes called the Gaia-Enceladus merger, after its discovery using Gaia satellite data, brought in roughly 10 billion solar masses of stars and dark matter. The collision disrupted the existing disk and deposited a significant fraction of the stellar halo population we see today. The quiet billions. After this tumultuous early period, the Milky Way entered a more quiescent phase over the last 8 to 10 billion years. The major mergers stopped, though minor mergers with dwarf galaxies continued and continue today. The galactic disk reformed and settled into a stable, rotating structure, supporting the beautiful spiral pattern we observe. Star formation continued steadily in the disk, fed by gas accreting from the surrounding halo and enriched by the products of stellar evolution. The Sun formed during this period, approximately 4.6 billion years ago, from a molecular cloud in the galactic disk that had been enriched by previous generations of stars. The fact that the Milky Way has remained relatively undisturbed for billions of years has important implications for life. Major galactic collisions can disrupt planetary systems, trigger intense bursts of star formation that flood the galaxy with radiation, and generally create environments hostile to the long-term stability needed for biological evolution. The Milky Way's quiet, recent history may be one reason why complex life had time to evolve on Earth. We benefited from billions of years of relatively stable galactic conditions, with our solar system remaining far from major disturbances in a calm region of the galactic disk. The role of gas accretion. For the Milky Way to maintain star formation over billions of years, it needs a continuous supply of fresh gas. The current reservoir of cold molecular gas in the galactic disk contains only enough material to sustain star formation for another billion years or so at the current rate. Yet the galaxy shows no signs of running out of fuel. The solution to this puzzle involves gas accretion from the surrounding halo and intergalactic medium. Streams of gas, some of it primordial material that has never been part of a star, continuously fall into the galactic disk, replenishing the supply of star-forming material. Some of this gas comes from the fountain-like circulation driven by stellar feedback. Supernovae and stellar winds heat gas in the disk, driving it upward into the halo as a hot outflow. This gas eventually cools and rains back down onto the disk, completing a circulation cycle that takes hundreds of millions of years. Additional gas accretes from the cosmic web, filaments of matter that connect galaxies throughout the universe. The Milky Way sits at the intersection of several of these filaments, allowing it to draw in fresh material from the surrounding intergalactic medium. This accretion brings not just gas, but also angular momentum that helps maintain the disk's rotation. High-velocity clouds. Evidence for ongoing gas accretion comes from observations of high-velocity clouds, concentrations of neutral hydrogen gas moving at speeds inconsistent with normal galactic rotation. These clouds, some containing millions of solar masses of material, are falling into the Milky Way from the halo. One of the largest high-velocity cloud complexes, called the Magellanic Stream, extends for more than 100 degrees across the sky. This stream consists of gas stripped from the large and small Magellanic clouds by the Milky Way's tidal forces, material that will eventually merge with the galactic disk and fuel future generations of star formation. When high-velocity clouds collide with the galactic disk, they can trigger bursts of star formation as the infalling gas compresses existing molecular clouds. These impacts may seed new spiral arm structures and create expanding shells of gas visible in radio observations, spiral arms and density waves. The Milky Way's magnificent spiral structure represents one of the most visually striking features of massive disk galaxies. From our embedded position within the disk, we can't directly see the spiral pattern, but we can map it by observing the distribution of young stars, star-forming regions, and molecular clouds. The spiral arms aren't fixed structures rotating with the galaxy. Instead, they're density waves, regions where stars and gas temporarily pile up as they orbit the galactic center. You can think of them like traffic jams on a circular highway, where cars slow down and bunch up, then speed up and spread out again. The density wave pattern rotates around the galaxy at a different speed than the stars themselves, a phenomenon called the spiral pattern speed. Stars and gas clouds pass through the spiral arms over the course of their orbits, spending more time in the arms because they slow down slightly in the enhanced gravitational field. This slowing down compresses the gas clouds passing through the spiral arms, triggering gravitational collapse and star formation. That's why spiral arms appear bright and blue in optical images of galaxies. They're outlined by the light of massive young stars and glowing nebulae, marking regions of active stellar birth. Our galactic neighborhood. The Sun orbits within the Orion Spur, sometimes called the Orion Arm, a minor spiral feature lying between two of the Milky Way's major spiral arms. Our nearest major spiral structure is the Perseus Arm, located about 6,500 light-years farther from the galactic center than our current position. In the other direction, moving toward the galactic center, we find the Sagittarius Arm about 5,000 light-years away. These distances place us in what might be considered the galactic suburbs, far enough from the crowded inner galaxy to enjoy relatively stable conditions, but close enough to benefit from the chemical enrichment provided by billions of years of stellar evolution. Our position in the galaxy likely influenced the development of life on Earth. Closer to the galactic center, the higher density of stars increases the probability of close stellar encounters that could disrupt planetary orbits. The radiation environment is also more intense near the galactic core, with frequent supernovae and active galactic nucleus activity during earlier epochs. Farther out in the galactic halo, the lower metallicity of stars means planets forming around those stars would contain fewer heavy elements, potentially making Earth-like rocky planets rarer. The reduced supernova rate in the outer galaxy might also mean less enrichment of the interstellar medium with biologically important elements like carbon, nitrogen, oxygen, and phosphorus. The galactic habitable zone. This concept has led some astronomers to propose the idea of a galactic habitable zone, a region of the Milky Way where conditions are most favorable for the development of complex life. This zone would exclude the inner galaxy due to stellar crowding and intense radiation, and also exclude the outer regions due to low metallicity and reduced chemical enrichment. The galactic habitable zone might form an annular region, a ring-shaped volume extending from perhaps 13,000 to 33,000 light-years from the galactic center. Our solar system's position, at approximately 26,000 light-years, places us squarely within this potentially habitable region, which may not be coincidental. However, the galactic habitable zone concept remains speculative and controversial. Life might be far more adaptable than we imagine, thriving under conditions we'd consider hostile, or specific local factors like the type of star, the presence of gas giant planets in protective orbits, or the history of impacts on a given planet might matter far more than galactic-scale consideration. Still, the concept highlights an important truth. The Milky Way isn't a uniform environment. Different regions offer vastly different conditions for planet formation, chemical composition, and long-term stability. The galaxy's enormous mass creates diverse ecological niches spanning hundreds of thousands of light-years, weighing the galaxy with satellites. Modern efforts to measure the Milky Way's total mass increasingly rely on observations of satellite galaxies and distant halo stars. These objects orbit far from the galactic center, where the dark matter halo dominates the gravitational field. Their velocities and positions directly probe the total mass distribution, including components we cannot see. The technique works similarly to how planets reveal the Sun's mass through their orbital motions. By measuring the speeds and distances of satellite galaxies and applying Kepler's laws of orbital mechanics, astronomers can calculate the total mass enclosed within those orbits. Recent studies using this method suggest the Milky Way's mass within a radius of about 300,000 light-years is approximately 1.5 trillion solar masses, with uncertainties of about 20 to 30%. This represents one of the most precise measurements of our galaxy's total mass, significantly more massive than estimates from just a decade ago. The increased mass estimate has important implications. It suggests the Milky Way and Andromeda galaxies may have more comparable masses than previously thought, with our galaxy potentially being the more massive of the two. This affects predictions about their future collision and merger, including the timing and dynamics of that cosmic encounter. Escape velocity and gravitational binding. The Milky Way's enormous mass creates a correspondingly enormous gravitational well. To completely escape the galaxy's gravitational pull from our current location, an object would need to achieve a velocity of approximately 550 kilometers per second. That's more than twice the Sun's current orbital velocity around the galactic center. This escape velocity demonstrates just how tightly the Milky Way's gravity binds objects within the galaxy. Even stars moving at several hundred kilometers per second remain gravitationally bound, destined to orbit the galactic center for billions of years. Only the most extreme events can accelerate stars to escape velocity. Hypervelocity stars, rare objects moving at speeds exceeding 1,000 kilometers per second, represent stars that have been gravitationally slingshot by interactions with the central supermassive black hole or through supernova explosions in tight binary systems. These stellar outcasts, hurling through the galactic halo on trajectories that will eventually carry them into intergalactic space, represent less than 1 in 100 million stars. The vast majority of the Milky Way's stellar population remains trapped in the galaxy's gravitational embrace, locked in orbits that will persist until the galaxy merges with Andromeda billions of years hence. The mass-luminosity mystery. One of the puzzling aspects of the Milky Way's mass is its mass-to-light ratio, the amount of mass per unit of luminosity. If we calculate the total light output from all the stars in the Milky Way, we find the galaxy shines with a luminosity of approximately 20 billion times the Sun's brightness. With a total mass of 1 trillion solar masses, this gives a mass-to-light ratio of about 50 solar masses per solar luminosity. In other words, for every unit of light the galaxy produces, there are roughly 50 units of mass, most of it invisible dark matter. This high mass-to-light ratio is typical of spiral galaxies and provides some of the strongest evidence for dark matter's existence. If the galaxy contained only stars, gas, and other normal matter, the mass-to-light ratio should be just a few solar masses per solar luminosity, reflecting the fact that stars convert only a small fraction of their mass into light over their lifetimes. The factor of 10 difference between the observed and expected mass-to-light ratios points directly to the presence of dark matter, invisible mass that contributes to the galaxy's gravitational field without producing light. Comparing galactic masses. How does the Milky Way's mass compare to other galaxies in the universe? This question provides important context for understanding whether our galaxy is typical or unusual in the broader cosmic landscape. The Milky Way ranks as a large galaxy by universal standards. Most galaxies in the observable universe are dwarf galaxies, systems containing less than a few billion solar masses. These small galaxies vastly outnumber their larger cousins, making the Milky Way's trillion solar masses quite impressive in relative terms. Among spiral galaxies specifically, the Milky Way falls into the category of large spirals, comparable in mass to other well-studied systems like Andromeda. However, even larger spiral galaxies exist. NGC 644, for example, contains approximately 1 trillion solar masses just in stars and gas, not counting dark matter, making it several times more massive than the Milky Way. The most massive galaxies in the universe are giant ellipticals found at the centers of galaxy clusters. These cosmic behemoths can contain 10 trillion solar masses or more, built up through hundreds of galaxy mergers over billions of years. Compared to these monsters, the Milky Way appears modest, though still far above average by universal standards. The local group mass budget. Within the local group, the Milky Way and Andromeda together account for approximately 3 trillion solar masses, roughly 90% of the group's total mass. The remaining 10% distributes among dozens of smaller galaxies, from systems like Triangulum with tens of billions of solar masses, down to ultra-faint dwarfs containing just a few thousand solar masses worth of stars. This mass distribution reflects a general principle of cosmic structure called hierarchical formation. Small structures form first, then gradually merge to build larger systems. The local group represents an intermediate-scale structure, more massive than individual galaxies, but much less massive than galaxy clusters that can contain thousands of galaxies and total masses of 100 trillion to 1 quadrillion solar masses. The local group isn't isolated, but forms part of an even larger structure called the Virgo supercluster, a vast web of galaxies spanning over 100 million light-years. Within this larger context, the Milky Way represents one galaxy among thousands, though still among the more massive individual systems. Dark matter halo substructure. Recent simulations of galaxy formation predict that the Milky Way's dark matter halo shouldn't be smooth and uniform. Instead, it should contain significant substructure in the form of dark matter clumps or subhalos, remnants of smaller dark matter concentrations that merged with the growing galaxy over billions of years. These predictions suggest the Milky Way's dark matter halo might contain hundreds or thousands of subhalos, ranging in mass from millions to billions of solar masses. Most of these subhalos would be completely dark, containing only dark matter without any stars. But some might host the ultra-faint dwarf galaxies discovered in recent surveys, tiny stellar systems containing just a few thousand stars. Detecting dark matter subhalos that contain no stars poses an enormous challenge since they emit no light and reveal their presence only through gravitational effects. However, astronomers have proposed several techniques that might work. One involves looking for gaps or distortions in stellar streams as they pass through the galactic halo. Dark matter clumps gravitationally perturbing these streams could create telltale patterns revealing the subhalo's mass and location. Another approach uses gravitational lensing, looking for cases where light from distant quasars or background galaxies is bent by intervening dark matter concentrations. By carefully analyzing these lensing signatures, researchers might detect dark matter subhalos even if they contain no visible matter. The cosmic web connection. The Milky Way's mass didn't assemble in isolation, but formed as part of the cosmic web, the large-scale structure of the universe, consisting of filaments, walls, and voids spanning billions of light-years. Dark matter formed the backbone of this structure, with normal matter following the dark matter's gravitational pull. The Milky Way sits within one of these cosmic filaments, a relatively dense region connecting massive galaxy clusters. Matter flows along these filaments, channeling gas and smaller galaxies toward larger structures like our own. This cosmic geography influences the Milky Way's growth, providing a continuous supply of infalling material that adds to the galaxy's mass over time. Measurements of galaxies' positions and velocities throughout our cosmic neighborhood reveal these large-scale motions. Everything within a few 100 million light-years, including the local group, is slowly falling toward the Virgo cluster, a massive concentration of galaxies located approximately 55 million light-years away, containing more than 1,000 galaxies and a total mass exceeding 1 quadrillion solar masses. This infall occurs at velocities of several hundred kilometers per second, adding to the galaxy's individual motions through space. On even larger scales, the local supercluster itself is being drawn toward an even more massive structure called the Shapley supercluster, demonstrating that even vast collections of galaxies remain subject to gravity's influence across cosmic distances. Measuring cosmic expansion and peculiar velocities. The Milky Way's motion through space results from a combination of cosmic expansion and peculiar velocity, the galaxy's motion relative to the expansion flow. While cosmic expansion carries distant galaxies away from us at speeds proportional to their distance, local gravitational interactions create additional motions called peculiar velocities. The Milky Way's peculiar velocity relative to the cosmic microwave background radiation, the afterglow of the Big Bang that provides our best reference frame for cosmic motion, is approximately 600 kilometers per second. This motion results from gravitational attraction toward overdense regions of the universe and repulsion from underdense voids. Understanding these motions helps astronomers map the distribution of matter throughout the universe, including dark matter that we cannot directly see. The pattern of peculiar velocities traces the underlying gravitational field, revealing where mass concentrates, even when that mass emits no light. The future, 4 billion years hence. Looking forward, the Milky Way's mass will continue to grow through ongoing mergers with satellite galaxies and accretion of intergalactic gas. But the most dramatic change awaits approximately 4 billion years in the future when the Milky Way and Andromeda galaxies collide. This event will transform both galaxies beyond recognition. Computer simulations of the merger show a complex dance as the two galaxies approach, pass through each other, separate briefly, then fall back together for a second and third passage. Each encounter strips stars and gas from both galaxies, creating long tidal tails stretching across millions of light-years. The merger process will take approximately 2 billion years from first contact to final coalescence. During this time, the night sky, as seen from Earth, if our planet survives, will be dramatically transformed. Andromeda, currently visible as a faint smudge, will grow to dominate the sky, eventually stretching across tens of degrees as the galaxy approaches. The two supermassive black holes at the centers of both galaxies will spiral together, eventually merging in an event that will release enormous energy in the form of gravitational waves. The combined black hole will have a mass of approximately 10 million solar masses, making it one of the most massive black holes in the local universe. The merged galaxy, Milkomeda, the final product of the Milky Way-Andromeda merger, will be a giant elliptical galaxy, a roughly spherical system lacking the spiral structure and active star formation of its progenitor galaxies. This new galaxy, sometimes playfully dubbed Milkomeda or Milkdromeda, will contain approximately 2 trillion solar masses distributed across a region several 100,000 light-years in diameter. Most of the gas in both galaxies will be consumed in intense bursts of star formation triggered by the merger. These starbursts will create brilliant blue regions visible across intergalactic distances, briefly making the merged system one of the brightest galaxies in the local universe. But once the gas is exhausted, star formation will essentially cease. The merged galaxy will slowly fade as its stellar population ages, with no new generations of stars to replace those dying off. Over hundreds of billions of years, Milkomeda will gradually redden as its most massive, brightest stars exhaust their fuel, leaving behind a population dominated by small, long-lived red dwarfs. The fate of our solar system. What happens to Earth and our solar system during this galactic collision? Despite the dramatic nature of the merger, the actual risk to our planet may be surprisingly low. Galaxies are mostly empty space, so the probability of direct stellar collisions remains minuscule even during a major merger. Computer simulations suggest approximately a 50% chance that our solar system will be flung into the outer regions of the merged galaxy, perhaps 50,000 to 80,000 light-years from the new galactic center. There's a roughly 3% chance we could be ejected entirely, hurled into intergalactic space, where we'd become part of a diffuse stellar halo surrounding Milkomeda. However, these gravitational disruptions pale in comparison to another threat facing Earth. The Sun is gradually brightening as it ages, and within approximately 1 billion years, the increased solar luminosity will make Earth's surface too hot for liquid water to exist. By the time the Milky Way and Andromeda collide, Earth will likely already be uninhabitable, baked sterile by our own star's evolution. If humanity or its descendants still exist in 4 billion years, they will either need to have migrated to other star systems or found ways to engineer planetary habitability under extreme conditions. From their perspective, wherever they might be, the galactic merger will be a spectacular cosmic show playing out over millions of years, beyond the local group. Even as the Milky Way and Andromeda merge, the larger cosmic evolution continues. The universe's expansion, driven by dark energy, is accelerating. This means that galaxy clusters and superclusters that are not gravitationally bound to our local group are receding faster and faster, eventually disappearing beyond an cosmic horizon beyond which light can never reach us. In approximately 150 billion years, assuming the current model of cosmic acceleration is correct, all galaxies outside our local group will have been carried so far away by expansion that their light can no longer reach us. Any civilizations existing in the far future living within the merged Milky galaxy, will look out and see an apparently empty universe with no hint that billions of other galaxies exist beyond their observable horizon. They might conclude they inhabit the only galaxy in an otherwise empty cosmos, unaware that they're simply isolated by cosmic expansion. Fortunately, we live in an era where the universe's richness remains visible, with billions of galaxies observable across cosmic time, providing windows into the universe's history and evolution. The role of mass in cosmic evolution. The Milky Way's mass represents more than just an impressive number. It encapsulates billions of years of cosmic history, from the earliest dark matter structures forming in the infant universe, through countless galaxy mergers and star formation episodes, to the majestic spiral galaxy we inhabit today. This mass creates the gravitational field that holds hundreds of billions of stars in coherent orbits, regulates the formation of new stellar generations, and will eventually determine the galaxy's fate as it merges with Andromeda. The mass distribution shapes everything from the rotation curve we observe to the spiral structure marking sites of star formation, to the tidal disruption of satellite galaxies providing forensic evidence of past mergers. Understanding the Milky Way's mass and how it's distributed provides crucial insights into galaxy formation and evolution more generally. Our galaxy serves as the best-studied example of a large spiral galaxy, the template against which we compare other similar systems throughout the universe. Unsolved mysteries remain. Despite tremendous progress in measuring and understanding the Milky Way's mass, major mysteries remain. The fundamental nature of dark matter, which comprises 80% or more of the galaxy's total mass, remains unknown, despite decades of intensive research. The exact mass of the Milky Way itself carries significant uncertainties, with different measurement techniques sometimes giving results that disagree by factors of 2 or more. Refining these measurements and understanding the sources of uncertainty represents an ongoing challenge for observational astronomy. The detailed structure of the dark matter halo, including whether it contains predicted substructure and how its density profile behaves in the innermost regions near the galactic center, remains poorly constrained. These details matter for dark matter detection experiments and for understanding galaxy formation theory. The complete merger history of the Milky Way has only recently begun to be reconstructed through archaeological studies of stellar populations. Each new analysis reveals previously unknown merger events, suggesting the galaxy's assembly history may be more complex than current models indicate. New observational windows. Future observations promise to address many of these mysteries. The Gaia spacecraft continues collecting data, with each new data release providing more precise measurements of stellar positions and motions for billions of stars. These measurements will enable increasingly detailed reconstructions of the galaxy's structure and history. New telescopes across the electromagnetic spectrum will probe different aspects of the Milky Way's structure and composition. Radio telescopes like the Square Kilometre Array will map the distribution of neutral hydrogen gas throughout the galaxy with unprecedented sensitivity, revealing the fuel supply for future star formation and tracing gas accretion from the intergalactic medium. Infrared observatories can peer through the dust that obscures much of the galactic disk in visible light, revealing stellar populations and star-forming regions hidden from optical telescopes. The James Webb Space Telescope is already providing spectacular views of star formation in nearby galaxies, techniques that can be applied to study similar processes within the Milky Way. X-ray and gamma-ray telescopes detect high-energy phenomena associated with compact objects like neutron stars and black holes, supernova remnants, and the energetic particles filling the galactic halo. These observations complement optical and infrared studies, building a multi-wavelength picture of the galaxy's structure and activity. Gravitational wave detectors are opening an entirely new window on the universe, detecting the mergers of black holes and neutron stars throughout the Milky Way and beyond. As these detectors become more sensitive, they'll reveal populations of compact objects we cannot detect through electromagnetic radiation alone, providing new constraints on stellar evolution and the galaxy's mass budget. Neutrino astronomy and the galaxy. Neutrino observatories offer yet another perspective on galactic processes. These ghostly particles, produced in nuclear reactions in stellar cores and in supernova explosions, pass through normal matter with barely any interaction. Detecting them requires enormous detectors filled with thousands of tons of water or ice, monitored by arrays of sensitive light detectors, watching for the faint flashes produced when neutrinos occasionally interact with atomic nuclei. Neutrinos from the Sun have been detected for decades, confirming our understanding of solar nuclear fusion. A handful of neutrinos from supernova 1987A, a stellar explosion in the Large Magellanic Cloud, visible from the southern hemisphere, provided crucial information about the supernova mechanism and validated theoretical models of stellar collapse. Future neutrino observatories with greater sensitivity may detect neutrinos from supernovae throughout the Milky Way, providing advance warning of stellar explosions and revealing details about the collapse process invisible through other means. They might even detect the diffuse background of neutrinos from all past supernovae throughout cosmic history, a faint glow that carries information about star formation and stellar death across billions of years. The search for dark matter continues. Perhaps the most exciting potential discoveries involve directly detecting dark matter particles. Experiments around the world are searching for these elusive particles using increasingly sensitive detectors. Some experiments look for the tiny energy deposits created when dark matter particles collide with atomic nuclei. Others search for the products of dark matter particle annihilation, or decay. If dark matter consists of a new type of particle, detecting it would revolutionize physics, confirming predictions of theories that extend beyond the standard model of particle physics. It would also provide crucial information about the nature of 80% of the Milky Way's mass, transforming our understanding of what the galaxy actually contains. Even negative results from these experiments provide valuable information, ruling out certain types of dark matter particles and guiding theorists toward more viable models. The ongoing search represents one of the most important experimental efforts in modern physics, with implications reaching far beyond the Milky Way to the nature of matter and energy throughout the universe. Citizen science and galactic exploration. Remarkably, amateur astronomers and citizen scientists contribute significantly to our understanding of the Milky Way. Projects like Galaxy Zoo allow volunteers to classify galaxy images, helping astronomers analyze datasets too large for individual researchers to handle. Similar projects focus on finding stellar streams, classifying variable stars, and identifying interesting objects in massive sky surveys. Amateur astronomers with backyard telescopes discover supernovae, comets, and asteroids. Their observations contribute to databases tracking stellar positions and brightnesses over time, providing long baseline measurements valuable for detecting subtle changes that reveal binary star systems, exoplanets, or variable stellar behavior. This democratization of astronomical research means that anyone with interest and dedication can contribute to expanding human knowledge about the galaxy we inhabit. The Milky Way's study isn't restricted to professional astronomers with access to major telescopes, but encompasses a worldwide community of observers and analysts working together to unravel cosmic mysteries. The philosophy of galactic scale. Beyond the scientific measurements and observations, contemplating the Milky Way's mass invites philosophical reflection on humanity's place in the cosmos. We inhabit a planet orbiting an ordinary star, one of hundreds of billions, in a galaxy that itself is one of hundreds of billions in the observable universe. The Milky Way's trillion solar masses represent a scale almost incomprehensible to human intuition. Light, the fastest thing in the universe, takes 100,000 years to cross the galaxy. The atoms in our bodies were forged in stellar furnaces and scattered through space in supernova explosions, cycled through multiple generations of stars before eventually incorporating into the cloud that formed our solar system. We are, in a very literal sense, made of star stuff. assembled from elements created in the nuclear furnaces of massive stars that lived and died within the gravitational embrace of the Milky Way. Every breath you take contains atoms that were once part of stars, that traveled through the interstellar medium for millions or billions of years before eventually becoming part of your body. Cosmic humility and wonder. This cosmic perspective can evoke simultaneous feelings of insignificance and profound connection. Yes, we're tiny compared to the galactic scale, ephemeral beings living for mere decades on a world that will exist for billions of years. Orbiting a star that's one of hundreds of billions in a galaxy that's one of hundreds of billions in the observable universe. Yet we're also the parts of the universe that have become conscious, capable of understanding and appreciating the cosmos that created us. We can measure the mass of the entire galaxy, trace its history across billions of years, and predict its future evolution. We can understand the nuclear physics that powers stars and the gravitational dynamics that organize galaxies. In a sense, through human consciousness, the Milky Way has become aware of itself. The atoms forged in stellar cores billions of years ago have organized themselves into beings capable of comprehending the cosmic processes that created them. That's a remarkable and perhaps unique achievement in our corner of the universe. The galactic perspective on human concerns. Viewing Earth and human civilization from a galactic perspective can also inform how we think about terrestrial challenges. From the Milky Way's vantage point, national borders are invisible, political disputes seem petty, and the division of humanity into competing factions appears tragically short-sighted. We're all inhabitants of a tiny world orbiting an ordinary star in the outer suburbs of a vast galaxy. The differences between human cultures, while significant at human scales, pale in comparison to the fundamental commonality of our species' existence on this fragile oasis of life. This perspective doesn't diminish the importance of human concerns. Your daily struggles, your relationships, your hopes and fears remain vitally important at human scales. But it provides context, a reminder that we share a common origin and common destiny as members of a species that evolved on this particular planet in this particular galaxy. Stewardship of our cosmic home. Understanding the Milky Way's scale and our place within it also highlights the preciousness of Earth. As far as we know, our planet hosts the only life in the galaxy. While statistical arguments suggest life might exist elsewhere among the hundreds of billions of stars, we have no confirmed evidence of biological activity beyond Earth. This makes our world extraordinarily valuable, not just to humanity, but potentially to the galaxy itself. If life is rare, then Earth represents something unique, a crucible of biological complexity that might be one of only a handful of such places in the entire Milky Way. This realization carries ethical weight. We're stewards not just of human civilization, but potentially of the only known life in a galaxy containing 1 trillion solar masses spread across 100,000 light-years. Preserving Earth's habitability and biological diversity becomes a cosmic responsibility, maintaining the conditions that allow consciousness and complexity to exist in an otherwise largely sterile galaxy. The long view, deep time and galactic futures. The Milky Way's history spans more than 13 billion years, from the first dark matter structures forming in the early universe to the mature spiral galaxy we observe today. That's more than twice as long as Earth has existed and nearly 1,000 times longer than humans have walked the planet. This deep time perspective reveals that the galaxy we see today represents just a snapshot in an ongoing story of cosmic evolution. The Milky Way was different in the past, smaller and more chaotic, with higher rates of star formation and more frequent galactic collisions. It will be different in the future, merging with Andromeda to form a giant elliptical galaxy, eventually fading as star formation ceases and stellar populations age. On these timescales, human civilization appears as the briefest flicker, a few thousand years of recorded history against billions of years of galactic evolution. Yet even this briefest flicker has produced beings capable of measuring the galaxy's mass, reconstructing its history, and predicting its future. That's an achievement worth celebrating, regardless of the cosmic scales involved. becoming a spacefaring civilization. If humanity survives and continues to develop technologically, we might eventually spread beyond Earth to become a true spacefaring civilization, inhabiting multiple star systems throughout the Milky Way. This remains speculative and faces enormous technical challenges, but it's at least theoretically possible. A civilization capable of interstellar travel could potentially colonize a significant fraction of the galaxy over timescales of millions to tens of millions of years. Even traveling at modest fractions of the speed of light, starships could reach nearby stellar systems in decades or centuries, establish new colonies, and send out additional expeditions to further systems. Over time, such a civilization could expand to encompass thousands, millions, or even billions of star systems, creating a galactic-scale culture spanning significant portions of the Milky Way's mass and volume. The challenges are immense, the distances vast, and the time required enormous, but nothing in known physics absolutely prevents such expansion. The Fermi paradox and galactic silence. This possibility raises one of the most intriguing questions in all of science. If spacefaring civilizations are possible, and if intelligent life arises on even a tiny fraction of the Milky Way's hundreds of billions of potentially habitable planets, where is everybody? This question, known as the Fermi paradox after physicist Enrico Fermi, who famously asked it, has no satisfactory answer. The galaxy is old enough that any civilization that arose even a few million years before humanity could potentially have spread across the entire Milky Way by now. Yet we see no evidence of such expansion, no signs of galactic engineering projects or interstellar civilizations, no clearly artificial signals detected by SETI searches. Various solutions to the Fermi paradox have been proposed. Perhaps life is much rarer than optimistic estimates suggest, making Earth one of very few inhabited worlds. Perhaps intelligent life commonly destroys itself before becoming spacefaring. Perhaps interstellar travel is more difficult than we imagine. Or perhaps advanced civilizations choose not to expand aggressively through the galaxy. Or perhaps we're simply looking in the wrong ways, or at the wrong times. The Milky Way is enormous, and humanity has been capable of detecting artificial signals for less than 1 century out of the galaxy's 13-billion-year history. We might be like someone standing on a beach, examining a handful of sand, and concluding the ocean contains no fish because none are visible in that particular sample. The search for extraterrestrial intelligence. Despite the lack of confirmed detections, the search for extraterrestrial intelligence continues. Radio telescopes scan the skies, listening for artificial signals that might indicate technological civilizations elsewhere in the galaxy. Optical SETI projects look for brief laser pulses that could serve as interstellar beacons. As exoplanet discoveries accumulate, revealing thousands of worlds orbiting other stars throughout the Milky Way, SETI researchers can target their searches toward potentially habitable planets, where technological civilizations might plausibly arise. The discovery of even a single confirmed extraterrestrial signal would revolutionize our understanding of life's place in the galaxy and potentially provide insights into how technological civilizations can survive and thrive over cosmic timescales. The Milky Way's enormous mass implies an enormous number of potential sites for life. If even 1 in a million stars hosts an inhabited planet, that still means hundreds of thousands of living worlds scattered throughout the galaxy. The question isn't whether life could exist elsewhere in such a vast structure, but whether we'll ever find evidence of it. Astrobiology and the galactic context. The emerging field of astrobiology approaches these questions by studying life's requirements and how they might be met on worlds throughout the galaxy. Every discovery about extremophiles on Earth, organisms thriving in conditions once thought too harsh for life, expands the potential habitable zone and increases the estimated number of worlds where life might exist. Discoveries of subsurface oceans on moons like Europa and Enceladus reveal that habitable environments might exist in places previously considered sterile. If life can arise in the dark oceans beneath ice-covered moons, then the number of potential habitats multiplies enormously, limited not just to planets in narrow circumstellar habitable zones, but potentially including moons throughout the outer reaches of stellar systems across the entire galaxy. The Milky Way's mass and chemical composition make it an excellent environment for life by cosmic standards. Billions of years of stellar evolution have enriched the interstellar medium with heavy elements necessary for rocky planets and complex chemistry. The galaxy's stable rotation and relatively quiescent recent history provide long periods of environmental stability needed for biological evolution. Understanding the distribution of elements throughout the Milky Way helps astrobiologists identify regions where Earth-like planets are most likely to form. The metallicity gradient, with higher heavy element abundances in the inner galaxy, suggests the inner disk might produce more rocky planets per star than the metal-poor outer regions. However, this must be balanced against other factors like radiation exposure and stellar density that might make inner regions less favorable for long-lived biospheres. The chemistry of life in a galactic context. Every living thing on Earth relies on complex chemistry involving carbon, hydrogen, oxygen, nitrogen, phosphorus, and other elements. These elements didn't exist in the early universe, which contained only hydrogen, helium, and trace amounts of lithium produced in the Big Bang. Every heavier element formed inside stars or in supernova explosions. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood. All these elements were synthesized in stellar furnaces over billions of years of galactic chemical evolution. The Milky Way's mass provided enough gravitational pull to retain this enriched material, rather than losing it to intergalactic space, allowing it to incorporate into new generations of stars and planets. This chemical enrichment occurred gradually over cosmic history. The first stars formed from nearly pure hydrogen and helium, and probably couldn't produce planets or life. Each subsequent stellar generation incorporated more heavy elements, gradually building up the chemical complexity necessary for worlds like Earth. Our solar system formed when the Milky Way was already over 8 billion years old, giving previous stellar generations time to enrich the local interstellar medium with the elements needed for rocky planets and biological chemistry. We're probably not among the first generations of potentially inhabited worlds in the galaxy, but neither are we necessarily among the last. Galactic dynamics and habitable zones over time. The Milky Way's structure has changed significantly over its history, which affects where and when habitable conditions might exist. In the galaxy's early history, higher rates of supernova explosions and stellar collisions might have made the inner regions hostile to life, while insufficient chemical enrichment might have prevented complex planet formation in the outer regions. As the galaxy matured and the rate of violent events declined, more regions became potentially habitable. The expansion of heavy elements to larger galactic radii over time means the habitable zone may have gradually moved outward, with regions like our solar system's location becoming favorable for life only in the galaxy's middle age. Future evolution will continue this trend. As the most massive stars exhaust their fuel and explode, the supernova rate will gradually decline. The merger with Andromeda will trigger a final burst of star formation, but afterward, the merged galaxy will slowly fade, with fewer and fewer new stars forming as the gas supply is exhausted. Eventually, in hundreds of billions of years, star formation will essentially cease. The galaxy will contain only long-lived red dwarf stars and the cooling remnants of dead stars, white dwarfs, neutron stars, and black holes. The window for life in the Milky Way, while billions of years long, is ultimately finite. Dark energy and the ultimate fate. On even longer timescales, the accelerating expansion of the universe driven by dark energy will shape the Milky Way's ultimate fate. Current models suggest that dark energy will eventually tear apart even gravitationally bound structures, though this occurs on timescales vastly longer than the current age of the universe. In approximately 10 to the 20th power years, roughly 100 billion times the current age of the universe, protons themselves may decay if certain theories of physics are correct. causing ordinary matter to disintegrate into radiation. On such unimaginable timescales, even the most stable structures eventually dissolve. But these far future considerations remain highly speculative, depending on physics we don't yet understand. For any foreseeable future, measured in billions rather than trillions of years, the Milky Way will continue to exist as a coherent structure, its trillion solar masses held together by gravity, hosting stars, and potentially life. Educational impact and public understanding. Understanding the Milky Way's mass and structure isn't just an academic exercise for professional astronomers. It represents one of humanity's great intellectual achievements, revealing our place in the cosmic order through careful observation, mathematical reasoning, and creative theoretical insight. This knowledge enriches human culture by providing context for our existence and perspective on our cosmic situation. Teaching students about the galaxy's scale and structure cultivates scientific literacy and critical thinking skills while inspiring wonder at the natural world. Popular science communication about the Milky Way has reached enormous audiences through documentaries, books, planetarium shows, and online content. These efforts make cutting-edge astronomical research accessible to the public, building support for scientific research and inspiring the next generation of scientists and engineers. The economics of galactic exploration. Studying the Milky Way also has practical implications. Space-based observatories like Hubble, Gaia, and the James Webb Space Telescope cost billions of dollars to develop and operate. Ground-based facilities like the Very Large Telescope arrays and the future Extremely Large Telescope represent major investments of national and international resources. These expenditures reflect a societal judgment that understanding the universe merits significant investment, even when immediate practical applications aren't obvious. The knowledge gained about the galaxy's structure, composition, and evolution may not directly improve daily life, but it expands human understanding and capability in ways that often lead to unexpected benefits. Technologies developed for astronomical research have found applications in medicine, communications, computing, and numerous other fields. The CCDs that capture astronomical images revolutionized digital photography. Techniques for analyzing astronomical data contribute to machine learning and artificial intelligence. Materials and engineering methods developed for space telescopes find uses in terrestrial applications. International collaboration in galactic science. Modern galactic astronomy operates as a thoroughly international enterprise. Major observatories involve collaborations among dozens of countries. Data from space missions is shared openly with researchers worldwide. International conferences bring together scientists from every continent to discuss new discoveries and theoretical developments. This collaborative structure reflects both practical necessity and idealistic vision. No single nation has the resources to fully explore the Milky Way's structure using every available technique across all wavelengths. International cooperation leverages complementary expertise and facilities, enabling research programs impossible for individual countries. The universal nature of scientific knowledge also encourages collaboration. The laws of physics work the same way everywhere, and understanding the Milky Way benefits all humanity regardless of national boundaries. This makes galactic astronomy an arena where international cooperation thrives, even when political relationships remain strained, training the next generation. Understanding the Milky Way's mass and structure appears in curricula from elementary schools through graduate programs in astrophysics. Students learn progressively more sophisticated concepts, from basic ideas about stars and galaxies in early education, through quantitative treatments of orbital mechanics and gravitational physics in undergraduate courses, to research-level investigations in graduate studies. This educational pipeline ensures continued progress in galactic astronomy as new generations of scientists build on previous work. Each cohort brings fresh perspectives and innovative techniques, gradually refining our understanding of the galaxy we inhabit. Many professional astronomers trace their inspiration to early experiences learning about the cosmos, whether through planetarium visits popular science books, or simply looking up at the night sky and wondering about what they saw. Maintaining public engagement with galactic astronomy helps ensure continued interest and support for research programs. Technological advances driving discovery. The history of galactic astronomy closely tracks technological development in telescopes, detectors, and data analysis techniques. Early studies relied on naked-eye observations and simple optical telescopes. Photographic plates enabled systematic sky surveys. Electronic detectors increased sensitivity and precision. Each technological advance opened new discovery space. Radio astronomy revealed the galaxy's structure in unprecedented detail by mapping hydrogen gas distributions. Infrared observations penetrated dust clouds that block visible light. X-ray and gamma-ray telescopes detected high-energy phenomena invisible to optical instruments. Modern astronomy increasingly relies on computational power for both observations and analysis. Massive sky surveys generate petabytes of data that must be processed, catalogued, and analyzed using sophisticated algorithms. Simulations of galaxy formation and evolution require supercomputers running for months to model billions of years of cosmic history. Future technological developments will continue this trend. Next-generation telescopes with unprecedented light-gathering power and angular resolution will reveal galactic structure at ever finer scales. More sensitive gravitational wave detectors will observe compact object mergers throughout the Milky Way. Improved particle physics experiments might finally detect dark matter directly, revealing the nature of most of the galaxy's mass. The role of theory and simulation. Understanding the Milky Way's mass requires not just observations, but also theoretical frameworks for interpreting those observations. Newton's law of gravitation and Kepler's laws of orbital motion provide the foundation for calculating mass from orbital velocities. Einstein's general relativity becomes necessary in strong gravitational fields like those near the central black hole. Computer simulations play an increasingly important role in galactic research. These simulations start with initial conditions representing the early universe, then evolve the system forward using gravitational physics and gas dynamics. The results can be compared with observations to test whether our theoretical understanding correctly predicts galactic properties. Modern simulations reproduce many observed features of galaxies like the Milky Way, including the formation of spiral arms, the segregation of stellar populations by age and composition, and the effects of dark matter on rotation curves. However, discrepancies remain, particularly at small scales, where observations sometimes don't match predictions. These discrepancies drive continued theoretical and observational work. Understanding why simulations fail to perfectly reproduce observations often leads to new insights about physical processes operating in galaxies. This iterative process between observation, theory, and simulation gradually improves our understanding of galactic structure and evolution. Interdisciplinary connections. Studying the Milky Way's mass connects to numerous other scientific disciplines. Nuclear physics explains how elements form in stellar cores and supernova explosions. Atomic and molecular physics describes the spectra of stars and gas clouds that allow us to measure their compositions and velocities. Particle physics proposes candidates for dark matter and predicts their properties. Computational science provides tools for analyzing massive datasets and running complex simulations. Applied mathematics applies the equations describing gravitational dynamics and stellar evolution. Engineering makes possible the telescopes and detectors that gather observational data. Even historical research contributes to galactic astronomy. Understanding how knowledge about the Milky Way developed over time provides insights into the scientific process and helps avoid repeating past mistakes. The history of astronomy serves as a case study in how human understanding of the natural world evolves through observation, theory, and debate. The aesthetic dimension. Beyond scientific understanding, the Milky Way inspires aesthetic appreciation and artistic response. The band of light stretching across dark skies has inspired poets, painters, musicians, and storytellers throughout human history. Every culture that could see the Milky Way developed myths and legends explaining its appearance. Modern understanding that this luminous band represents our view through the galactic disk, seeing billions of distant stars whose light blends together, adds rather than detracts from the aesthetic experience. Knowing we're looking at a structure containing 1 trillion solar masses spanning 100,000 light-years enhances the sense of wonder and beauty. Astronomical images from space telescopes provide stunning visual experiences that combine scientific information with artistic composition. False color images, mapping different wavelengths to visible colors, reveal structures invisible to human eyes while creating compositions of genuine beauty. These images appear in art galleries alongside more traditional artworks, blurring boundaries between science and art. Cultural impact and mythology. The Milky Way appears in mythologies worldwide, with different cultures offering diverse explanations for the band of light across the night sky. Greek mythology explained it as milk spilled from the breast of the goddess Hera. Norse legends saw it as the path souls traveled to reach Valhalla. Chinese astronomy called it the Silver River, a celestial waterway separating lovers. Modern scientific understanding doesn't erase these cultural meanings, but adds layers of significance. We now know the Milky Way isn't just a visual phenomenon, but a massive physical structure that shaped the formation of our solar system and made our existence possible. This deepens rather than diminishes its significance. The name Milky Way itself preserves ancient mythology in modern scientific discourse. Astronomers could have adopted a purely technical designation, but instead retained a poetic name connecting current knowledge to thousands of years of human wonder at the night sky. Personal connection to cosmic scale. For most of human history, people lived under dark skies where the Milky Way blazed overhead on clear nights, a constant reminder of the cosmos beyond Earth. Modern light pollution has erased this experience for billions of people living in urban areas who may never see the Milky Way with their own eyes. This represents a genuine loss. The direct visceral experience of seeing the galaxy's structure provides connection to the cosmic context of human existence that photographs and planetarium shows can't fully replicate. The band of light overhead communicates in an immediate way that we inhabit a galaxy containing hundreds of billions of stars. Preserving dark sky sites and advocating for responsible outdoor lighting helps maintain this connection. Many people find their first experience seeing the Milky Way from a truly dark location to be profound and memorable, shifting their perspective on humanity's place in the universe. Summary of key insights. Let's draw together the major themes explored throughout this journey into the Milky Way's mass and structure. We've seen that our galaxy contains approximately 1 trillion solar masses, making it one of the larger galaxies in the universe, though far from the most massive. This enormous mass divides into visible components: stars, gas, dust, and planets, comprising perhaps 20% of the total, with the remaining 80% consisting of mysterious dark matter. The visible galaxy spans 100,000 light-years across, organized into multiple structural components, including a central bulge, thin and thick disks showing spectacular spiral structure, a diffuse stellar halo, and an extended dark matter halo reaching far beyond the visible edge. At the very center sits Sagittarius A*, a supermassive black hole with 4 million solar masses that shapes the orbits of nearby stars through its intense gravitational field. The Milky Way's mass didn't appear instantly, but accumulated over more than 13 billion years through continuous growth and mergers with smaller galaxies. This violent history continues today as the galaxy consumes satellite systems like the Sagittarius dwarf elliptical galaxy. In the future, the most dramatic event will be the collision and merger with Andromeda approximately 4 billion years hence, creating a giant elliptical galaxy containing 2 trillion solar masses. The significance of dark matter. Perhaps the most profound implication of studying the Milky Way's mass is what it reveals about the nature of matter itself. The fact that 80% of the galaxy consists of dark matter, a substance we cannot see and barely understand, highlights how much remains unknown about the physical universe. This dark matter shaped galaxy formation throughout cosmic history, providing the gravitational scaffolding around which normal matter accumulated. Without dark matter, galaxies like the Milky Way couldn't exist. The universe would look completely different, possibly lacking the structures necessary for stars, planets, and life to form. Solving the dark matter mystery remains one of the great challenges in modern physics. Success would revolutionize our understanding of fundamental particles and forces, potentially revealing new physics beyond the standard model. It would also complete our understanding of what the Milky Way actually contains, explaining the nature of most of the galaxy's mass. The living galaxy. Throughout this exploration, we've emphasized that the Milky Way isn't a static structure, but a dynamic, evolving system. Gas continuously cycles through the interstellar medium, forming new stars that eventually die and return enriched material to space. Small galaxies fall inward and merge with the larger structure, adding mass and triggering bursts of star formation. The spiral arms rotate as density waves, organizing star formation on galactic scales. This ongoing evolution means the galaxy we see today differs from its past state and will differ from its future configuration. Understanding galactic dynamics requires thinking in terms of cosmic time, billions of years over which entire stellar populations form, evolve, and die, while the overall galactic structure gradually changes. The Milky Way serves as a cosmic ecosystem where matter cycles through different states and structures, creating the chemical complexity necessary for planets and life. We exist within, and because of this system, our bodies built from atoms, processed through multiple generations of stellar evolution. Humanity's place in the galactic story. Our species exists at a particular moment in the Milky Way's history, approximately 13.7 billion years after the Big Bang and 13 billion years after our galaxy began forming. We evolved on a planet orbiting a middle-aged star in the galactic suburbs, in a relatively calm and stable region well suited for the development of complex life. This privileged position in space and time allowed human civilization to emerge and eventually develop the capacity to study the very galaxy that created the conditions for our existence. We've measured the Milky Way's size and mass, traced its history, and predicted its future evolution, a remarkable achievement for a species that has existed for less than 1/1,000,000th of the galaxy's lifetime. Whether we're alone in possessing this knowledge remains unknown. The Milky Way's enormous size and long history suggest many opportunities for life and intelligence to emerge elsewhere among the hundreds of billions of stars. Yet we've detected no confirmed evidence of other technological civilizations. This absence might indicate we're unique, or simply that we haven't yet learned how to recognize the signs of extraterrestrial intelligence. Either possibility carries profound implications. If we're alone, then Earth hosts something precious beyond measure, the only known consciousness in a galaxy of 1 trillion solar masses. If we're one among many, then the galaxy teems with diverse forms of intelligence, each with unique perspectives on existence and perhaps knowledge we can scarcely imagine. The measurement challenge continues. Despite decades of research using increasingly sophisticated techniques, determining the Milky Way's exact mass remains challenging. Different measurement methods sometimes produce results that disagree by factors of 2 or more. This uncertainty reflects the fundamental difficulty of weighing a structure from inside it using indirect gravitational traces. Future observations, particularly from missions like Gaia and next-generation telescopes, promise to refine these measurements. Each improvement in precision helps constrain models of galaxy formation and the nature of dark matter. Even after centuries of astronomical study, we're still discovering new aspects of our galactic home. This ongoing process of discovery demonstrates that science doesn't provide complete answers all at once. Instead, understanding develops gradually through accumulation of observations, refinement of theories, and occasional revolutionary insights that reshape entire fields. The Milky Way's mass represents a question with progressively better answers, but perhaps never a final definitive value given the complexity of defining where a galaxy ends. The galaxy as laboratory. The Milky Way serves as an irreplaceable laboratory for studying galaxy formation and evolution. Because we're located inside it, we can observe individual stars and gas clouds in far greater detail than possible for external galaxies millions of light-years away. This detailed view allows tests of theoretical predictions about stellar evolution, star formation, and galactic dynamics impossible to perform in more distant systems. Every star we can observe in detail, every molecular cloud we can map, every stellar stream we can trace through the halo provides data points for understanding how galaxies work. These observations then inform our interpretation of external galaxies, where we can't resolve individual components, but must infer internal structure from integrated light. This unique perspective makes the Milky Way crucial for cosmology, beyond just understanding our local galaxy. The physics operating in our galaxy should work the same way in distant galaxies across the universe. By studying these processes locally in exquisite detail, we learn universal principles applicable across cosmic scales. Interdependence of galactic components. Throughout this exploration, we've seen how different components of the Milky Way interconnect in complex ways. The dark matter halo's gravity shapes stellar orbits throughout the visible galaxy. Star formation in the disk depends on gas supply regulated by flows between disk and halo. Chemical enrichment from dying stars affects the composition of later stellar generations. The supermassive black hole at the galactic center, despite containing just 4 million solar masses, influences the surrounding stellar population and may regulate star formation in the central molecular zone through energetic feedback. The spiral arms organize star formation through density wave compression of molecular clouds. This interdependence means understanding the Milky Way requires considering it as an integrated system rather than a collection of separate components. Changes in one region propagate throughout the structure over millions or billions of years. The galaxy exhibits emergent properties that arise from interactions among components rather than from any single element. Comparative galactic anatomy. Comparing the Milky Way to other galaxies reveals both typical and unusual features. Our galaxy's mass places it among large spirals, comparable to Andromeda, though perhaps slightly less or more massive depending on which measurements you trust. This makes the Milky Way representative of an important class of galaxies found throughout the universe. The spiral structure, star formation activity, and central black hole all appear typical for galaxies of similar mass. However, some aspects may be unusual. The Milky Way's satellite galaxy population seems somewhat sparse compared to theoretical predictions, a discrepancy known as the missing satellites problem that remains an active research area. The galactic warp, a distortion of the outer disk that bends above and below the main galactic plane, might result from tidal interactions with satellite galaxies or from the shape of the dark matter halo. Similar warps appear in other spiral galaxies, suggesting common dynamical processes operating across galactic populations. The mass-energy equivalence. Einstein's famous equation, E equals mc squared, reminds us that mass and energy are equivalent, interchangeable aspects of the same underlying reality. The Milky Way's trillion solar masses therefore represent not just matter, but an enormous reservoir of energy, potentially accessible through matter-energy conversion. If all the Milky Way's mass could somehow be converted to energy, it would release approximately 10 to the 64th power joules, an almost incomprehensible amount of energy, dwarfing the total output of every star in the observable universe over cosmic timescales. Of course, no known process could achieve such complete conversion, and even if possible, it would destroy the galaxy in a cataclysmic explosion. This thought experiment illustrates the enormous energy content locked in matter. Even tiny fractions of mass converted to energy release tremendous power, as demonstrated by stars, where nuclear fusion converts about 0.7% of the mass involved into radiation over billions of years. Gravitational potential energy. The Milky Way's mass also represents enormous gravitational potential energy. Objects separated by the galaxy's scale possess huge amounts of energy due to their positions in the gravitational field. This energy becomes available when objects fall together, releasing it as kinetic energy and eventually as heat and radiation. Galaxy mergers tap this gravitational potential energy reservoir, converting it to kinetic energy of motion and eventually to radiation through shock heating of gas and increased star formation. The upcoming merger with Andromeda will release gravitational potential energy comparable to the total energy output of trillions of stars over millions of years. This energy drives much of the dynamic activity in the universe. Gas falling into galaxies, stars forming from collapsing clouds, black holes accreting matter, all these processes convert gravitational potential energy into other forms, powering phenomena from stellar luminosity to the most energetic explosions in the cosmos. The information content of the galaxy. Beyond mass and energy, the Milky Way contains information, patterns, and structures that carry meaning. The positions and velocities of stars encode the galaxy's dynamical history. Chemical compositions preserve records of nucleosynthesis processes. Stellar streams map ancient merger events. If intelligent life exists on other worlds throughout the galaxy, then the information content increases enormously. Every civilization would develop unique cultures, sciences, arts, and philosophies, each representing distinct solutions to the challenge of making sense of existence. The total information stored in billions of potential biospheres could exceed anything imaginable from a single world's perspective. Even without invoking life, the galaxy contains vast information in physical structures. The precise trajectories of hundreds of billions of stars, each influenced by every other mass in the galaxy through gravity, represent a computational problem of staggering complexity. The state of the galaxy at any moment encodes unimaginable amounts of information about positions, velocities, compositions, and internal states of countless objects. The privileged epoch. We live in what cosmologists call the stelliferous era, the epoch when stars actively form and shine, lasting roughly from a few 100 million years after the Big Bang until perhaps 100 trillion years in the future. This represents only a tiny fraction of the universe's potential lifespan, extending far beyond current stellar activity. Within this epoch, we exist at a particularly interesting time for galactic astronomy. The universe has expanded enough that we can observe billions of galaxies across cosmic distances, studying galaxy evolution over much of cosmic history. Yet the accelerating expansion driven by dark energy hasn't yet carried most distant galaxies beyond our observational horizon. Future civilizations trillions of years hence might find themselves unable to study external galaxies at all, with expansion having removed all but the closest gravitationally bound neighbors from view. They would face much greater challenges in understanding cosmic history and structure than we do today. We're also privileged to live during the era when major surveys like Gaia are revolutionizing galactic astronomy, when new telescopes are revealing exoplanets around other stars in our galaxy, when gravitational wave astronomy is opening entirely new observational windows. It's an exciting time for galactic exploration and discovery. The responsibility of knowledge. With understanding comes responsibility. Knowing the Milky Way's scale and structure, recognizing our place within this vast cosmic system, creates obligations to preserve and extend human knowledge for future generations. The insights gained through centuries of astronomical research represent collective achievements of our species. This knowledge base grows through continued investment in science education, research facilities, and space missions. Each generation builds on previous work, gradually extending the boundaries of human understanding. Maintaining this continuity requires conscious effort and resource allocation. Beyond preserving existing knowledge, we have opportunities to vastly expand our understanding of the galaxy. Questions about dark matter's nature, the prevalence of life, the detailed merger history of the Milky Way, and countless other topics await answers. Future discoveries will reveal aspects of our galactic home we cannot yet imagine. The cosmic context for ethics. Understanding the Milky Way's immense scale and our tiny place within it influences philosophical and ethical thinking. Some find cosmic scales overwhelming, leading to nihilistic conclusions that nothing matters given our insignificance. Others find inspiration and meaning, seeing human consciousness as remarkable precisely because it can comprehend and appreciate the vast universe that created it. The cosmic perspective can inform ethical reasoning by highlighting our common humanity. From a galactic vantage point, the divisions that separate human groups appear trivial. We're all inhabitants of one small world, sharing common origins and facing common challenges, orbiting one star among hundreds of billions in a galaxy we're only beginning to understand. This perspective doesn't solve ethical dilemmas, but it provides context. Issues that seem overwhelmingly important at human scales appear differently when viewed against cosmic time and space. Conversely, some concerns like existential risks threatening all life on Earth gain additional weight when you consider that this planet might host the only known life in the galaxy. Looking forward, the next century of discovery. The next century promises extraordinary advances in our understanding of the Milky Way's mass and structure. Missions already planned or under development will provide revolutionary data. The European Space Agency's Gaia mission will continue releasing progressively more precise measurements of stellar positions and motions. Future missions might extend this work, mapping even more stars with greater accuracy. Ground-based observatories like the Extremely Large Telescope, with its 39-meter primary mirror, will resolve individual stars in crowded regions like the galactic center and globular clusters, tracing stellar motions with unprecedented precision. The Square-Kilometer Array radio telescope will map hydrogen gas throughout the galaxy, revealing the fuel supply for future star formation. Gravitational wave detectors will detect thousands of black hole and neutron star mergers throughout the Milky Way, constraining models of stellar evolution and compact object formation. Neutrino observatories will capture particles from supernovae and other high-energy events, providing unique insights into processes invisible to electromagnetic observations. Dark matter detection experiments might finally succeed in directly observing these mysterious particles, answering questions about the nature of 80% of the galaxy's mass. Even negative results will constrain theoretical possibilities, gradually eliminating incorrect models and pointing toward viable alternatives. The human element in discovery. Behind every astronomical discovery are people, scientists dedicating careers to understanding the cosmos. Astronomers spending nights at telescopes gathering data, theorists developing mathematical models, engineers designing innovative instruments, programmers writing analysis software, all contribute to expanding human knowledge about the Milky Way. These individuals come from diverse backgrounds, bringing varied perspectives and approaches to scientific problems. International collaboration brings together complementary expertise, enabling projects impossible for any single nation or institution. This collective effort represents humanity at its best, working together to answer fundamental questions about our place in the universe. Students entering astronomy today will spend careers using instruments and techniques not yet invented, making discoveries we cannot yet anticipate. They'll build on current understanding while challenging assumptions and exploring new possibilities. Science progresses through this succession of generations, each extending the work of predecessors. The public's galaxy. The Milky Way belongs not just to professional astronomers but to everyone. It's our cosmic home, the structure that shaped conditions allowing our existence. Public interest in galactic astronomy remains strong, with documentaries, books, and online content reaching millions. This public engagement benefits science by building support for research funding and inspiring future scientists. It also enriches culture by connecting people to the cosmos and providing perspective on humanity's place in nature. Understanding that we're made of star stuff, that we inhabit a galaxy of hundreds of billions of suns, changes how we see ourselves and our world. Citizen science projects allow public participation in actual research, from classifying galaxies to searching for exoplanets to identifying stellar streams. These projects democratize science while harnessing collective human effort to analyze datasets too large for professional researchers alone. the poetic and the quantitative. Throughout this exploration, we've balanced quantitative precision with qualitative appreciation. The Milky Way's mass can be expressed as approximately 1 trillion solar masses, a precise measurement subject to ongoing refinement. But numbers alone don't capture the grandeur of a structure 100,000 light-years across, containing hundreds of billions of stars, serving as home to at least one technological civilization. Science and poetry need not oppose each other. The most effective communication about the galaxy combines rigorous data with evocative language that conveys not just facts, but also meaning. Numbers provide precision, but metaphors and analogies make abstract concepts concrete and memorable. The Milky Way is simultaneously a gravitationally bound system of approximately 1 trillion solar masses extending across 100,000 light-years, and a river of stars flowing through the night sky, each star potentially hosting worlds where unknown forms of life might look up at their own skies and wonder about their place in the cosmos. Concluding reflections. We've journeyed through the Milky Way's structure from the central supermassive black hole to the diffuse dark matter halo extending hundreds of thousands of light-years into space. We've seen how the galaxy's trillion solar masses accumulated over more than 13 billion years through mergers and accretion, how it continues to evolve today, and how it will ultimately merge with Andromeda to create an even more massive structure. The visible components, stars, gas, dust, and planets, account for less than 20% of the total mass. The remainder consists of dark matter, an invisible substance we detect only through gravitational effects. This mysterious component dominates the galaxy's mass budget and shaped its formation, yet we still don't know what it actually is. Solving this mystery remains one of the great challenges in modern physics. Understanding the Milky Way's mass matters for reasons both scientific and philosophical. Scientifically, it constrains models of galaxy formation, tests our understanding of gravity and dark matter, and provides context for interpreting observations of distant galaxies across cosmic history. Philosophically, it reveals our place in a vast cosmic structure, one galaxy among billions in the observable universe. The weight of stars and darkness. When we speak of the Milky Way's mass, we're really discussing two distinct components whose natures differ profoundly. The visible matter, stars, gas, and dust, consists of atoms, particles whose properties we understand through quantum mechanics and nuclear physics. This ordinary matter behaves according to well-established physical laws, emitting and absorbing light, clumping together to form stars and planets, undergoing nuclear fusion and radioactive decay. The dark matter component remains far more mysterious. It interacts through gravity, but apparently not through electromagnetism, passing through ordinary matter with barely any interaction. It doesn't emit, absorb, or reflect light at any wavelength. We infer its presence entirely from gravitational effects on visible matter and on the structure of space-time itself. These two components coexist within the galaxy but inhabit somewhat different spatial distributions. The visible matter concentrates in the thin galactic disk, especially in spiral arms where star formation actively proceeds. The dark matter distributes more spherically, forming an extended halo that provides the gravitational scaffolding supporting the entire structure. Together, these components create a stable system that has persisted for billions of years, despite the chaotic motions of individual stars and the violent processes of star formation and death. The Milky Way's trillion solar masses maintain coherence across timescales longer than the age of Earth itself. The galaxy's influence on cosmic structure. The Milky Way doesn't exist in isolation, but forms part of larger cosmic structures stretching across hundreds of millions of light-years. Its gravitational influence shapes the local group, determining the motions of dozens of smaller galaxies orbiting within its gravitational sphere. Beyond the local group, the Milky Way participates in bulk flows driven by even larger mass concentrations. We're falling toward the Virgo cluster at several hundred kilometers per second, part of a general motion of galaxies throughout our cosmic neighborhood, responding to the gravitational attraction of overdense regions and repulsion from underdense voids. These motions reveal the distribution of matter on scales far larger than individual galaxies. By mapping peculiar velocities throughout our region of the universe, astronomers reconstruct the matter distribution, including dark matter concentrations that emit no light. The Milky Way's mass contributes to this larger structure, adding its gravitational pull to the complex web of forces shaping cosmic evolution. Timescales of change. The Milky Way evolves on multiple timescales, from the rapid motions of individual stars to the glacially slow changes in overall structure. Stars orbit the galactic center on timescales of hundreds of millions of years. Our Sun has completed only about 20 orbits since Earth formed, yet the galaxy appeared nearly modern even on the Sun's first circuit. Star formation occurs continuously, but varies in intensity, responding to gas availability and external triggers like galaxy mergers. The current rate of a few solar masses per year has persisted for billions of years, with only gradual decline as gas supplies are slowly exhausted. Major mergers temporarily boost star formation rates by factors of 10 or more, creating spectacular starbursts visible across cosmic distances. Chemical enrichment proceeds gradually as successive generations of stars synthesize heavy elements and return them to the interstellar medium. The metallicity gradient we observe today developed over billions of years through differential star formation rates in inner versus outer galactic regions. The dark matter halo likely changes most slowly, its structure set primarily during the galaxy's formation and modified only by major mergers. Unlike visible matter that can dissipate energy through radiation and settle into compact configurations, dark matter remains diffuse, maintaining the extended halo structure established in the early universe. The role of feedback processes. Understanding galactic mass distribution requires accounting for feedback processes where energy and momentum from stars affect surrounding gas and subsequent star formation. Massive stars produce powerful stellar winds that sweep up surrounding material. Supernova explosions blast holes in the interstellar medium, driving hot gas into the galactic halo. These feedback processes regulate star formation, preventing it from proceeding too efficiently. Without feedback, galaxies would convert all their gas into stars very quickly, producing systems unlike what we observe. The balance between gas inflow, star formation, and feedback-driven outflows maintains the relatively stable star formation rates observed in galaxies like the Milky Way. The supermassive black hole also contributes feedback, particularly during active phases when significant accretion occurs. Energy released by infalling matter can drive powerful winds and jets that heat surrounding gas, potentially suppressing star formation in the central regions. The Fermi bubbles, extending above and below the galactic plane, may represent evidence of past feedback episodes from the central black hole. Magnetic fields and angular momentum. Two additional factors shape galactic structure beyond gravity alone. Magnetic fields, though weak, influence gas dynamics and star formation throughout the disk. These fields likely originated from seed fields in the early universe, amplified by billions of years of galactic rotation and turbulent motions in a process called the dynamo effect. Angular momentum, the rotational equivalent of linear momentum, determines why the Milky Way forms a disk rather than a sphere. As the protogalaxy collapsed under gravity, conservation of angular momentum forced material into a rotating disk where centrifugal force balances gravitational attraction. Dark matter, having little angular momentum, remained in a spherical halo, while normal matter settled into the disk. Understanding how galaxies acquire and redistribute angular momentum during formation remains an active research area. Mergers can add or remove angular momentum, affecting disk properties. Interactions with satellite galaxies transfer angular momentum through tidal torques, potentially influencing spiral structure and bar formation. The central bar structure. Speaking of bars, the Milky Way possesses a prominent bar-shaped structure in its central regions, a feature shared by roughly 2/3 of disk galaxies. This bar consists of stars orbiting in elongated paths aligned with the bar's long axis, creating a rectangular structure extending several thousand light-years from the galactic center. The bar influences gas flows in the inner galaxy, funneling material toward the center, where it can fuel star formation or feed the central black hole. It also affects stellar orbits throughout the inner disk, trapping some stars in resonant orbits, while scattering others to larger radii. Bars form through gravitational instabilities in rotating disks, a natural consequence of disk dynamics rather than requiring external triggers. Once formed, bars can persist for billions of years, though their strength may vary over time. The Milky Way's bar appears quite prominent and likely influences much of the galaxy's inner dynamics. Metallicity and chemical tagging. The distribution of heavy elements throughout the Milky Way carries detailed information about the galaxy's formation history. By measuring chemical compositions of thousands of stars, astronomers practice chemical tagging, identifying groups of stars with similar composition that likely formed together in the same molecular cloud. This technique reveals stellar populations too dispersed to recognize through spatial clustering alone. Stars born together may drift apart over billions of years until they're scattered across the galaxy, but they retain their distinctive chemical fingerprints. Finding these scattered siblings helps reconstruct ancient star formation events and trace gas flows through the galaxy over cosmic history. Different elements form through different nuclear processes, so measuring multiple elemental abundances provides detailed information. Alpha elements like oxygen and magnesium form primarily in massive stars and appear quickly after star formation begins. Iron forms primarily in type Ia supernovae from exploding white dwarfs, appearing on longer timescales. The ratio of alpha elements to iron, therefore, indicates how rapidly star formation proceeded in a given population. Stellar kinematics reveal history. The motions of stars encode information about galactic history complementary to chemical compositions. Stars in the thin disk generally move on circular orbits close to the galactic plane, reflecting their formation in a settled disk. Thick disk and halo stars show larger random velocities and often move on highly elliptical or even retrograde orbits, signatures of formation in external galaxies later accreted by the Milky Way. By combining chemical and kinematic information, astronomers can identify distinct stellar populations representing different formation environments and epochs. Some populations clearly originated in dwarf galaxies accreted billions of years ago. Others formed in situ within the Milky Way's disk. Still others represent intermediate cases where it's difficult to determine formation location with certainty. This stellar archaeology provides our most detailed view of how the Milky Way assembled over cosmic history. Unlike external galaxies where we see snapshots from different epochs, we can study individual stars within our galaxy, measuring their detailed properties and reconstructing the environments where they formed billions of years ago. The mass function of satellites. The Milky Way hosts dozens of confirmed satellite galaxies, ranging from the relatively massive Large Magellanic Cloud, containing about 10 billion solar masses, down to ultra-faint dwarfs with just a few thousand solar masses of coming stars. This satellite population provides crucial tests of dark matter theories and galaxy formation models. Simulations predict that dark matter halos, like the Milky Way's, should contain hundreds or thousands of smaller subhalos, remnants of dark matter concentrations that merged with the growing galaxy. However, we observe far fewer satellite galaxies than these predictions suggest, a discrepancy called the missing satellites problem. Several solutions have been proposed. Perhaps many dark matter subhalos contain no stars, remaining completely dark and therefore undetectable by optical surveys. Perhaps feedback processes prevent star formation in low-mass halos, producing fewer visible satellites than the number of dark matter subhalos. Or perhaps our models of dark matter are incorrect, requiring modifications that reduce predicted subhalo numbers. Recent discoveries of additional ultra-faint satellites in deep surveys suggest some missing satellites were simply undetected rather than non-existent. As surveys improve, we may find many more faint satellites, partially resolving the discrepancy. However, it's unlikely that observations will match theoretical predictions exactly without some refinements to either dark matter models or our understanding of how low-mass halos form stars. Precision cosmology from galactic observations. Measurements of the Milky Way contribute to cosmology, the study of the universe's origin, evolution, and ultimate fate. The galaxy's properties reflect initial conditions in the early universe and billions of years of evolution under the laws of physics. By comparing observations with simulations, we test cosmological models and constrain fundamental parameters. For example, the abundance of satellite galaxies around the Milky Way depends on the spectrum of density fluctuations in the early universe, a prediction of inflation theory. The chemical composition of the oldest stars constrains nucleosynthesis in the first stars and the timing of cosmic chemical enrichment. The stellar halo's structure and kinematics reveal the masses of accreted satellites which connect to the growth of cosmic structure over time. The local dark matter density, measured from stellar motions near the Sun, matters for direct detection experiments attempting to observe dark matter particles. In these ways, detailed studies of our galactic home inform our understanding of cosmic evolution on the largest scales. The Milky Way serves as both a unique detailed laboratory and a representative example of galaxy formation throughout the universe. The ultimate limits of knowledge. Despite continuing advances, some aspects of the Milky Way may remain forever uncertain. We can never view our galaxy from outside, seeing its spiral structure directly as we do for external galaxies. Our embedded perspective provides exquisite detail but makes large-scale structure difficult to determine. The far side of the galaxy, beyond the galactic center from our vantage point, remains difficult to observe. Dust extinction and stellar crowding complicate observations in that direction. Radio and infrared observations penetrate the dust, but provide different information than optical studies. Fully mapping the far side with precision comparable to our local neighborhood may remain challenging. The dark matter distribution, particularly at small scales, may never be directly observable. If dark matter particles don't interact with normal matter except through gravity, we must infer their distribution indirectly from gravitational effects. This works for large-scale structure, but becomes ambiguous at small scales, where multiple mass distributions might produce similar observable effects. The galaxy's history before the oldest surviving stars formed is largely inaccessible to direct observation. We can infer early conditions from models and from studying ancient stars, but we cannot observe the first generation of stars or the proto-galactic fragments that merged to form the Milky Way's core. This early history survives only in indirect traces. The continuing adventure. Yet these limitations don't diminish the excitement of galactic astronomy. Each question answered raises new questions. Each new observational capability reveals unexpected phenomena requiring explanation. The adventure of understanding our cosmic home continues with each new discovery. Recent findings, like the Gaia-Enceladus merger, the Fermi bubbles, and numerous stellar streams, demonstrate that major discoveries about the Milky Way's structure and history continue even after centuries of study. We're still learning fundamental things about the galaxy we inhabit, still finding surprises in data from new instruments and surveys. Future generations will build on current knowledge, extending understanding in directions we cannot yet anticipate. They'll use technologies not yet invented to answer questions we haven't yet thought to ask. The Milky Way's complexity ensures that galactic astronomy will remain a vibrant research field for centuries to come. Final thoughts on mass and meaning. We've explored the Milky Way's mass from multiple perspectives, as a measurement of approximately 1 trillion solar masses, as a gravitational field binding hundreds of billions of stars, as a dark matter concentration that shaped galaxy formation, as a chemical factory producing the elements necessary for life. Each perspective reveals different aspects of the same magnificent cosmic structure. This mass isn't just an abstract number, but has profound consequences. It determined how the galaxy formed and evolved over billions of years. It creates the gravitational environment enabling stellar orbits that have remained stable since before Earth existed. It represents the accumulated product of countless stellar generations, merger events, and gas accretion episodes spanning cosmic history. For us as individuals, the Milky Way's mass provides context for existence itself. We live within a gravitational system so vast that light takes 100,000 years to cross it, yet so precisely balanced that stars maintain coherent orbits for billions of years. We're made from atoms forged inside stars that were themselves part of this galactic system, connected through an unbroken chain of nuclear reactions and stellar evolution to the galaxy's earliest epochs. Understanding the Milky Way's mass represents one of humanity's great intellectual achievements, combining careful observation, mathematical reasoning, and creative theoretical insight to weigh a structure that encompasses hundreds of billions of suns. This knowledge enriches our civilization and reveals our place in the cosmic order, an invitation to wonder. As we conclude this journey through the Milky Way's mass and structure, I invite you to carry this knowledge with you. The next time you look up at a dark sky and see the Milky Way stretching overhead, remember that you're seeing billions of distant stars, each perhaps hosting its own planetary systems, all bound together by gravity into a structure containing 1 trillion times the mass of our Sunday. Remember that most of what holds this structure together remains invisible and mysterious, dark matter, whose nature we're still working to understand. Remember that this galaxy has existed for more than 13 billion years and will continue for billions more, eventually merging with Andromeda to create an even more massive structure. Remember that every atom in your body was processed through the nuclear furnaces of stars within this galaxy, that you're literally made of Milky Way star stuff, connected through physics and chemistry to cosmic processes operating on scales that dwarf human comprehension. Let this knowledge enhance rather than diminish your sense of meaning and purpose. Yes, we're tiny compared to galactic scales, but we're also the means by which the galaxy has become aware of itself. Through human consciousness, matter organized into a pattern capable of understanding the very processes that created it. That's not insignificance. That's profound significance of a different kind, the significance that comes from being part of something vastly larger than ourselves while possessing the capacity to comprehend and appreciate that larger context. Closing reflections. The Milky Way's trillion solar masses represent more than just the sum of its parts. This isn't merely a collection of stars and dark matter scattered randomly through space. It's an organized system with structure and history, a cosmic ecosystem where matter cycles through different states, where stars are born and die, where heavy elements form and disperse, where planets may host life and intelligence, contemplating the nature of existence. Understanding this system, measuring its mass, tracing its history, and predicting its future represents a remarkable achievement for a species that has existed for less than 1/1,000,000th of the galaxy's lifetime. We've used tools ranging from simple telescopes to orbiting observatories, employed physics from Newtonian gravity to general relativity and quantum mechanics, and developed theoretical frameworks capable of explaining observations spanning cosmic scales. Yet much remains unknown. The nature of dark matter, the complete merger history of the galaxy, the distribution of life among the stars, and countless other questions await future discoveries. Each generation of astronomers builds on previous work while opening new frontiers of understanding. The Milky Way will continue to reveal its secrets to those who study it with patience, creativity, and dedication. Each new instrument, each innovative observational technique, each theoretical breakthrough adds pieces to the grand puzzle of understanding our cosmic home. The journey of discovery never truly ends, but rather transforms, with each answer raising new and deeper questions. As we stand on Earth, looking up at the river of stars flowing across the night sky, We're witnessing something our ancestors saw but could not fully comprehend. They knew the Milky Way as a luminous band stretching overhead, inspiring myths and legends across cultures and millennia. We now know it as a gravitationally bound system of 1 trillion solar masses, a spiral galaxy 100,000 light-years across our home in the vastness of space. This knowledge doesn't diminish the beauty or wonder of the Milky Way. If anything, it enhances them. Understanding the physical processes behind the cosmic spectacle adds layers of meaning to the visual experience. The scattered light of billions of distant suns becomes a window into galactic structure, stellar evolution, and the chemical enrichment that made our existence possible. The numbers tell stories. Let's return once more to that fundamental measurement: 1 trillion solar masses. This number emerged from decades of painstaking observations, measuring stellar velocities, tracking satellite galaxy orbits, mapping gas distributions, and modeling gravitational dynamics. It represents countless hours of telescope time, mountains of data, and generations of scientific effort. But beyond the measurement itself, this number tells stories. It tells of dark matter halos forming in the early universe, creating gravitational wells that attracted normal matter. It tells of countless small galaxies merging over billions of years, building larger structures through cosmic violence. It tells of continuous star formation creating new suns, while old ones die and enrich the interstellar medium with heavy elements. It tells of spiral density waves organizing star formation on galactic scales. It tells of a central supermassive black hole growing through accretion and mergers. It tells of our solar system forming from an enriched molecular cloud, orbiting steadily through the galactic disk for 4.6 billion years while life evolved on Earth. Every fraction of that trillion solar masses has its own history, its own journey through cosmic time. Some dark matter particles have orbited the galactic center billions of times since the universe was young. Some atoms in stellar atmospheres formed in the Big Bang, cycled through multiple generations of stars, and will continue their journey through future stellar generations. Some molecules in interstellar space will eventually collapse to form new stars and planets, perhaps hosting future life that will look up at its own night sky and wonder about its place in the cosmos, just as we do today. The science of exploration. The methods used to determine the Milky Way's mass exemplify the scientific process at its best. Unable to directly measure the galaxy's mass by placing it on a cosmic scale, astronomers developed indirect techniques using gravity as a natural measuring instrument. By observing how objects move within the galactic gravitational field, whether stars in the disk, globular clusters in the halo, or satellite galaxies in distant orbits, scientists can infer the mass creating that gravitational field. This requires understanding orbital mechanics, applying Newton's laws and Einstein's relativity, accounting for uncertainties in distance and velocity measurements, and carefully modeling the mass distribution. Different measurement techniques sometimes yield somewhat different results, highlighting the uncertainties inherent in the process. Rather than discarding inconsistent measurements, scientists work to understand why different methods disagree, often leading to improvements in technique or theory. This self-correcting aspect of science, where disagreements drive refinement rather than being swept under the rug, ensures steady progress toward more accurate understanding. The increasing precision of mass measurements over recent decades demonstrates this process in action. Early estimates ranged across factors of several, with large uncertainties. Modern measurements using Gaia data and improved modeling techniques have narrowed the uncertainties substantially, converging toward values around 1 trillion solar masses with errors of perhaps 20 to 30%. Future observations will continue this refinement, potentially revealing whether the Milky Way's mass tilts toward the lower end near 700 billion solar masses or the higher end near 1.5 trillion solar masses. This precision matters for comparing our galaxy to cosmological simulations and understanding how typical or unusual the Milky Way might be among galaxies of similar luminosity. The artistry in science. While grounded in rigorous mathematics and careful observation, galactic astronomy also involves creativity and artistry. Deciding which observations to make, designing innovative experiments, finding clever ways to extract information from limited data, all require creative thinking as much as technical expertise. The visualizations astronomers create to communicate their findings blend science and art, translating abstract data into images that convey both information and aesthetic appeal. False color images, mapping different wavelengths, three-dimensional renderings of galactic structure, animations showing evolution over billions of years, all serve both scientific and artistic purposes. Even the mathematical models describing galactic dynamics possess a certain elegance. Equations that capture complex physical processes in compact symbolic form. There's beauty in the way Newton's inverse square law of gravity determines orbital motions, in how conservation of angular momentum shapes disk formation, in the symmetries that simplify complex calculations. Scientists often speak of elegant theories or beautiful solutions, revealing an aesthetic dimension to their work beyond pure functionality. The most satisfying explanations don't just match observations, but do so in ways that feel insightful and illuminating, revealing underlying order in apparent complexity. Education and inspiration. Knowledge about the Milky Way's mass and structure flows beyond professional astronomy into education at all levels. Children learn that stars cluster into galaxies and that we live inside one such galaxy. Secondary students encounter quantitative descriptions of galactic structure and practice calculations involving cosmic distances and masses. University students study galactic dynamics in detail, working through the mathematical frameworks describing rotating systems and gravitational fields. This educational progression builds scientific literacy across populations, helping people understand their cosmic context and appreciate the methods scientists use to investigate the universe. Even those who don't pursue scientific careers benefit from understanding how we know what we know about the galaxy we inhabit. The inspirational aspect matters as much as the educational. Many professional astronomers trace their career choices to early experiences that sparked fascination with the cosmos. A trip to a planetarium, a telescope view of Saturn's rings, a popular science book about galaxies. These experiences plant seeds that sometimes grow into lifelong passions and scientific careers. By communicating astronomical discoveries to broad audiences, scientists ensure that future generations will include individuals inspired to continue exploring the Milky Way and the wider universe. This creates a virtuous cycle where research generates public interest, which supports continued research, which generates new discoveries that inspire the next generation. International scientific cooperation. Modern galactic astronomy operates as a thoroughly international enterprise, with researchers from dozens of countries collaborating on major projects. The Gaia spacecraft represents a European-led mission, but data from it benefits astronomers worldwide. Ground-based observatories often involve consortia from multiple nations, sharing construction costs and observing time. This international cooperation reflects both practical necessity and idealistic commitment to science as a universal human endeavor. No single country possesses all the resources and expertise needed to fully explore galactic structure. Pooling resources and talents enables projects impossible for individual nations. The cooperative model also demonstrates that humans can work together towards shared goals despite political differences. Scientific collaboration continues, even when diplomatic relationships face challenges. The universal nature of scientific knowledge creates common ground, allowing researchers from diverse backgrounds to communicate through the shared language of mathematics and physics. This aspect of scientific culture offers hope for addressing other global challenges requiring international cooperation. If humanity can successfully collaborate to understand the Milky Way's trillion solar masses, perhaps we can also cooperate to address climate change, prevent conflicts, and build a more peaceful and prosperous world. The role of failure and uncertainty. The path to understanding the Milky Way's mass includes numerous failures and false starts alongside successes. Early estimates proved inaccurate when better data became available. Theoretical models sometimes failed to match observations, requiring revision or abandonment. Proposed explanations for phenomena like the rotation curve anomaly often turned out to be incorrect. Far from representing flaws in the scientific process, these failures drove progress. Each incorrect idea eliminated led closer to correct understanding. Each failed prediction revealed gaps in theoretical frameworks, motivating improved models. Uncertainty and revision characterize science at its frontiers, where knowledge transitions from unknown to known. Acknowledging uncertainty honestly represents scientific strength rather than weakness. When astronomers state that the Milky Way's mass is approximately 1 trillion solar masses with 30% uncertainty, they're being precise about the limits of current knowledge. This allows future observations to confirm, refine, or potentially overturn present understanding. Science progresses not by claiming absolute certainty, but by gradually reducing uncertainty through accumulation of evidence and refinement of theories. The Milky Way's mass has gone from barely constrained guesses a century ago to reasonably precise measurements today, with continuing improvements expected as observational techniques advance. Connections to human experience. Abstract as discussions of galactic mass might seem, they connect to human experience in multiple ways. The atoms composing our bodies originated in stellar nucleosynthesis within the Milky Way, making us literally part of the galaxy's mass inventory. The Sun's orbit through the galactic disk potentially influences Earth's climate and biological evolution through varying exposure to cosmic rays and spiral arm passages. The long-term stability of our solar system's galactic orbit depends on the overall mass distribution of the galaxy. If the Milky Way were significantly less massive, orbital dynamics might be less stable, potentially leading to encounters with other stars or ejection into intergalactic space over billions of years. Even our ability to observe and study the universe depends on living in a galaxy with particular properties. The chemical enrichment enabling rocky planet formation, the relatively calm galactic suburbs where our solar system orbits, the transparent atmosphere we've maintained, all these factors trace back to conditions shaped by galactic mass and structure. In this sense, understanding the Milky Way's mass helps explain the preconditions for our own existence. We find ourselves in a universe, and within a galaxy, compatible with our presence not by cosmic coincidence, but because only such conditions allow observers to arise and ask questions about their cosmic context. The anthropic consideration. This observation leads to anthropic reasoning, the recognition that observed properties of the universe must be compatible with the existence of observers. If the Milky Way had vastly different mass or structure, we likely wouldn't exist to study it. This doesn't mean the galaxy was designed for us, but rather that we necessarily find ourselves in circumstances compatible with our existence. This reasoning has limits and controversies. Some argue it explains apparent fine-tuning in physical constants and cosmological parameters. Others consider it a tautology that doesn't really explain anything. Regardless of philosophical stance, the anthropic observation remains valid. We study a galaxy whose properties allow our existence. This connects to broader questions about whether the universe contains other galaxies hosting life and intelligence. The Milky Way's properties, while necessary for our existence, likely aren't unique. Similar galaxies throughout the universe presumably offer similar opportunities for planet formation and biological evolution. If life arises commonly under favorable conditions, then countless other civilizations might exist throughout the cosmos, each studying their own home galaxies and wondering about their place in the universe. If life is rare, we might represent one of very few, or even the only technological civilization in our galactic neighborhood, making human existence extraordinarily precious and worth preserving. The value of basic research. Studying the Milky Way's mass exemplifies basic research motivated by curiosity rather than immediate practical application. No one measures the galaxy's mass to solve engineering problems or develop new technologies, at least not directly. The motivation comes from fundamental desire to understand the universe we inhabit. Yet history shows that basic research often yields unexpected practical benefits. Technologies developed for astronomical observations find applications in medicine, communications, computing, and countless other fields. The intellectual frameworks developed to understand galactic dynamics contribute to computational methods used across scientific disciplines. More broadly, basic research drives economic growth and technological progress in ways difficult to predict in advance. Societies that invest in fundamental science create knowledge and capability that enables future innovations impossible to imagine when the original research was conducted. The value of understanding the Milky Way's mass therefore transcends any immediate practical application. It represents investment in human knowledge and capability, expanding our understanding of nature and developing expertise applicable to unforeseen future challenges. Looking to the deep future. Projecting billions of years into the future, the Milky Way's mass will continue evolving through mergers and star formation. The collision with Andromeda represents the next major event. But even afterward, the merged galaxy will continue accumulating smaller satellites and converting gas into stars. Eventually, on timescales of tens to hundreds of billions of years, star formation will essentially cease as gas supplies are exhausted. The galaxy will fade as massive short-lived stars disappear, leaving populations dominated by small red dwarfs that can shine for trillions of years. White dwarfs, neutron stars, and black holes will accumulate as stellar remnants, representing the end states of stellar evolution. On even longer timescales, beyond 100 trillion years, even the longest-lived stars will exhaust their fuel. The galaxy will become dark, containing only stellar remnants, planets, and cold gas. If protons decay, as some theories predict, even these remnants will eventually dissolve into radiation over timescales measured in 10 to the 35th power years or longer. These far future considerations remind us that the Milky Way, as we know it, filled with shining stars and active star formation, represents a temporary phase in cosmic evolution. We live during the brief cosmic epoch when galaxies actively shine, a window that will eventually close as the universe ages and evolves into states we can barely imagine. The cosmic perspective on time. This deep time perspective challenges human intuition about permanence and change. The Milky Way seems eternal from human perspective, essentially unchanged over recorded history. Yet cosmic history reveals it as a dynamic, evolving structure, different in the past and destined to change dramatically in the future. The trillion solar masses we measure today accumulated gradually over 13 billion years and will continue evolving for trillions more. Our snapshot observations capture one moment in an ongoing story, like a single frame from a cosmic film spanning inconceivable durations. This perspective applies equally to human civilization. Our entire recorded history spans a few thousand years, barely perceptible against cosmic timescales. All of human experience, from the first agricultural settlements to modern technological civilization, occupies less than 1/1,000,000th of the galaxy's current age. Yet brief as our existence may be cosmically, it's no less real or meaningful for that brevity. The trillion solar masses of the Milky Way existed for billions of years before humans evolved, but those years lacked conscious observers to appreciate and understand them. In a sense, we give meaning to cosmic history by becoming aware of it. The privilege of consciousness. Consciousness itself represents one of the universe's most remarkable phenomena, as far as we know relatively rare and localized. Matter organized into patterns capable of self-awareness, of understanding the physical laws governing its own behavior, of contemplating its place in cosmic history. Human consciousness allows the Milky Way to know itself, examining its own structure through beings composed of atoms forged in its stellar furnaces. When we measure the galaxy's mass, study its dynamics, trace its history, we're not external observers but internal components, the galaxy's self-examination made manifest. This reflexive quality adds philosophical depth to astronomical research. We're simultaneously subject and object, observer and observed, part of the system we study, yet capable of transcending our local perspective to grasp the larger context. Whether other forms of consciousness exist elsewhere in the galaxy remains unknown. But even if we're alone, or one among few, consciousness remains cosmically significant. It transforms the universe from mere matter and energy following physical laws into a realm of meaning, understanding, and appreciation. The continuing narrative. As we bring this exploration toward closure, recognize that the story of the Milky Way's mass and structure continues beyond this presentation. New observations are being made tonight, new data being analyzed, new theoretical insights being developed. The scientific understanding presented here represents current knowledge but will be refined, extended, and perhaps revolutionized by future discoveries. This ongoing nature of scientific inquiry makes it exciting. We don't have complete final answers, but rather progressively better approximations, punctuated by occasional revolutionary insights that reshape entire fields. The Milky Way will continue revealing its secrets to those who study it with dedication and creativity. Future generations will look back at our current understanding, the way we look back at 19th century astronomy, recognizing both the genuine achievements and the limitations imposed by available technology and conceptual frameworks. They'll build on our work while surpassing it, extending human knowledge in directions we cannot yet imagine. A personal invitation. I encourage you to take this knowledge and make it personally meaningful. The next clear night, go outside away from bright lights if possible. Look up and find the Milky Way stretching across the sky. Let your eyes adjust to darkness and appreciate the band of combined light from billions of distant stars. Remember as you look that you're seeing the galaxy from inside, viewing the combined light of stars in the galactic disk. Remember that what you see represents less than 20% of the mass actually present, with the rest consisting of invisible dark matter revealed only through gravitational effects. Remember that this structure took more than 13 billion years to assemble, that it will merge with Andromeda in 4 billion years, that every atom in your body was processed through stars within this galactic system. Let that knowledge enhance your appreciation of the spectacle overhead. Consider sharing this experience with others. Point out the Milky Way to children, explaining that each faint patch of light represents thousands or millions of distant suns. Discuss with friends what it means to live inside a structure so vast, yet be able to comprehend and measure it. Let the cosmic perspective inform your thinking about life, meaning, and humanity's place in the universe. Gratitude for the journey. Thank you for joining me on this extended exploration of the Milky Way's mass and structure. We've covered enormous conceptual ground, from the basic measurement of approximately 1 trillion solar masses, through discussions of dark matter, galactic evolution, stellar populations, future mergers, and philosophical implications. We've covered enormous conceptual ground, from the basic measurement of approximately 1 trillion solar masses, through discussions of dark matter, galactic evolution, stellar populations, future mergers, and philosophical implications. We've examined the science behind the measurements, the history of discoveries, and the future prospects for deeper understanding. This journey reflects the cumulative achievement of countless astronomers, physicists, and other scientists over generations. Every measurement we discussed, every theoretical insight we explored, represents human intellectual effort extending across centuries. From Galileo's first telescopic observations to the Gaia spacecraft's precision astrometry, from Newton's gravity to Einstein's relativity, from spectroscopy to gravitational wave detection, each advance built on previous work. The knowledge we've explored isn't owned by any individual or institution, but belongs to all humanity as part of our collective understanding of nature. It's preserved in scientific literature, taught in universities, communicated through popular media, and applied in ongoing research programs. This knowledge will continue growing and evolving long after our current generation passes. The inexhaustible mystery. Despite everything we've learned about the Milky Way's mass and structure, mystery remains. The fundamental nature of dark matter, comprising 80% of the galaxy's mass, remains unknown. The detailed history of the galaxy's assembly from smaller fragments is still being reconstructed. The prevalence of life among the hundreds of billions of stars remains uncertain, with profound implications for our understanding of biology's place in the cosmos. These mysteries don't represent failures of science, but rather frontiers of knowledge, regions where our understanding transitions from known to unknown. They provide motivation for continued exploration, opportunities for future discoveries that may revolutionize our understanding as profoundly as dark matter's discovery transformed 20th century astronomy. The inexhaustible quality of these mysteries ensures that galactic astronomy will remain vibrant and exciting indefinitely. Each answer raises new questions. Each solved problem reveals new puzzles. The quest to understand our cosmic home will continue as long as human curiosity persists. Synthesis of scales. Throughout this exploration, we've moved fluidly between scales, spanning dozens of orders of magnitude, from subatomic particles to the entire galactic system. Dark matter particles measured in electron volts connect to galactic masses measured in solar masses. Individual stellar orbits combine to reveal overall gravitational fields. Atoms forged in stellar cores accumulate to create chemical gradients across thousands of light years. This synthesis of scales represents one of science's great achievements, the ability to connect phenomena at vastly different scales through unifying physical principles. The same gravitational force that makes apples fall on Earth governs stellar orbits in galaxies. The same nuclear physics that powers laboratory fusion reactors creates elements in stellar cores. The same quantum mechanics describing atomic structure explains stellar spectra. Understanding the Milky Way's mass requires integrating knowledge across all these scales, recognizing how microscopic processes aggregate to produce macroscopic structures. This integration demonstrates the unity of physical law, how the same fundamental principles operate throughout the universe, regardless of scale. The democratic nature of wonder. While technical understanding of galactic mass requires sophisticated mathematics and physics, appreciation and wonder remain accessible to everyone. You don't need advanced degrees to feel awe at the Milky Way's grandeur or to contemplate your connection to cosmic processes. The emotional and philosophical impact of understanding our place in the galaxy transcends technical expertise. This democratic quality of wonder matters because it connects astronomical knowledge to broader human experience. Science illuminates nature not just for specialists, but for everyone willing to engage with its findings. The Milky Way belongs to all of us as our cosmic home, regardless of scientific background or technical training. Popular science communication plays a vital role in making astronomical discoveries accessible beyond specialist communities. Books, documentaries, podcasts, and online content translate technical research into forms comprehensible to general audiences. This democratization of knowledge enriches culture and ensures broad public appreciation for scientific achievements. The economic investment in knowledge. Understanding the Milky Way's mass required enormous investments in telescopes, spacecraft, detectors, and human expertise. These investments come from public funding supporting basic research, reflecting societal decisions that understanding the universe merits significant resources despite uncertain immediate practical returns. This investment model recognizes that knowledge has intrinsic value beyond economic utility. Understanding the galaxy we inhabit represents a worthy goal, even absent direct technological applications. The knowledge gained enriches human culture, expands our intellectual horizons, and occasionally yields unexpected practical benefits. Countries and institutions that invest in basic scientific research create competitive advantages in education, technology, and innovation. They attract talented scientists, train skilled workforces, and position themselves at the frontiers of human knowledge. These benefits, though difficult to quantify precisely, justify continued investment in exploring our cosmic context. Lessons from galactic astronomy. Beyond specific facts about mass and structure, studying the Milky Way teaches broader lessons applicable across science and life. It demonstrates the power of persistent observation, how patient accumulation of data over decades or centuries reveals patterns invisible in short-term studies. It shows the value of multiple independent measurement techniques, how cross-checking results with different methods builds confidence in conclusions. It illustrates the importance of theoretical frameworks for organizing and interpreting observations. Raw data alone doesn't reveal meaning. Theoretical models provide context that transforms measurements into understanding. The interplay between observation and theory, each informing and constraining the other, drives scientific progress. It highlights how uncertainty and revision characterize knowledge at frontiers. Current understanding represents our best approximations given available evidence, subject to refinement as new data arrives. Accepting uncertainty honestly while continuing to pursue better understanding exemplifies mature scientific thinking. These lessons extend beyond astronomy. The scientific approaches developed to understand galactic mass apply to investigating any complex system where direct measurement proves difficult. The intellectual habits cultivated through scientific research, careful observation, logical reasoning, quantitative analysis, skeptical evaluation, serve well in many domains beyond professional science. The spiritual dimension. For many people, understanding the Milky Way's scale and their place within it carries spiritual significance. Contemplating cosmic vastness and our tiny place within it can evoke feelings of profound connection, humility, and transcendence that resemble religious or mystical experiences. This spiritual dimension doesn't require supernatural beliefs. The sense of connection to something larger than ourselves, the recognition of our ultimate insignificance against cosmic scales, combined paradoxically with the significance of consciousness and understanding, these realizations can be deeply moving regardless of religious background. Different people interpret these feelings differently. Some see them as pointing toward divine intelligence or cosmic purpose. Others view them as natural responses of evolved brains confronting scales far beyond those our cognitive systems evolved to comprehend. Both interpretations can coexist with scientific understanding of galactic structure and evolution. The Milky Way can serve as a source of meaning and inspiration, whether you interpret it through religious, philosophical, or purely naturalistic frameworks. Its grandeur transcends specific belief systems, offering opportunities for reflection and wonder accessible across worldviews. Responsibility to future generations. We've inherited understanding of the Milky Way from previous generations, who invested effort and resources in astronomical research. This creates obligations to preserve and extend that knowledge for future generations who will inherit it from us. Maintaining observatories, supporting research programs, training new scientists, and communicating discoveries to broad audiences ensures continuity of astronomical knowledge across generations. This intergenerational project of understanding the cosmos represents one of humanity's noblest endeavors, transcending individual lifespans and national boundaries. Future generations will build on our work as we built on our predecessors. They'll use technologies we're developing now and benefit from data being collected by current missions. The responsibility to provide them with solid foundations, accurate measurements, well-tested theories, and unsolved problems to tackle should inform how we approach galactic research today. This long-term perspective encourages careful work, thorough documentation, and honest acknowledgement of uncertainties. It recognizes that scientific understanding develops over timescales longer than individual careers, requiring sustained commitment from scientific communities and supporting institutions. The poetic closure. As we close this extensive journey through the Milky Way's mass and structure, return once more to the simple experience of looking up at the night sky. The band of light stretching overhead, visible from dark locations, inspired wonder long before anyone understood what they were seeing. Ancient humans saw the Milky Way and created myths to explain its presence. Medieval scholars debated whether it consisted of distant stars or some atmospheric phenomenon. Renaissance astronomers resolved it into individual stars with early telescopes. Modern scientists measure its mass at 1 trillion suns and trace its history across billions of years. Yet, despite all this accumulated knowledge, the fundamental experience of wonder remains unchanged. The Milky Way still inspires awe, still prompts contemplation of our place in the cosmos, still connects us to something vastly larger than individual human concerns. We've added layers of understanding to that ancient experience of wonder without diminishing it. Knowing that we see billions of distant stars doesn't make the sight less beautiful. Understanding that dark matter dominates the galaxy's mass doesn't reduce the mystery. Tracing the galaxy's 13 billion-year history doesn't eliminate the miracle of existence. If anything, knowledge enhances appreciation. The Milky Way becomes more wondrous, not less, when we understand what we're actually seeing and what it means for our existence. Each layer of understanding adds depth to experience, without replacing the fundamental emotional and aesthetic impact. A beginning, not an end. This conclusion marks not an ending but a transition. The exploration of the Milky Way's mass and structure continues beyond this presentation, in observatories around the world and in space, in computer simulations modeling galactic evolution, in classrooms where students learn about their cosmic home, in the minds of anyone who looks up at the night sky and wonders. Your engagement with this material might end here, or it might represent a beginning. Perhaps you'll seek out darker skies to better see the Milky Way. Perhaps you'll read additional books or watch documentaries exploring galactic astronomy. Perhaps you'll share what you've learned with others, spreading appreciation for our place in the cosmos. Perhaps some readers will be inspired to pursue scientific careers, becoming the next generation of astronomers who will extend our understanding beyond current limits. Or perhaps you'll simply carry this knowledge with you as context for existence, letting the cosmic perspective inform how you think about life, meaning, and humanity's place in the universe. The final word. The Milky Way contains approximately 1 trillion solar masses distributed across 100,000 light-years, consisting primarily of dark matter supplemented by hundreds of billions of stars, vast clouds of gas and dust, and untold numbers of planets. This structure, assembled over more than 13 billion years through mergers and continuous growth, hosts our solar system in a relatively calm suburban location, and will eventually merge with the Andromeda galaxy to form an even more massive structure. These facts, accumulated through centuries of careful observation and creative theoretical work, reveal our cosmic context. We live within a vast gravitational system that shaped the formation of our planet and made our existence possible. We're made from atoms processed through the galaxy's stellar population, connected through physics and chemistry to cosmic processes operating across unimaginable scales. Understanding this context doesn't answer all questions about existence, meaning, or purpose, but it provides a foundation, a scientific grounding for contemplating our place in nature. The Milky Way's trillion solar masses represent not just a measurement, but a connection to cosmic history, a reminder of the vast structure within which human drama unfolds. May this knowledge enrich your life, deepen your appreciation for existence, and perhaps inspire you to look up at the night sky with new understanding and renewed wonder. The Milky Way waits overhead, inviting contemplation and study, offering beauty and mystery in equal measure, connecting each of us to the cosmos that created us. The galaxy spins on through space and time, carrying us with it on a cosmic journey whose destination remains unknown. But knowing that we're part of this magnificent structure, understanding something of its nature and history, represents a profound achievement. We are, quite literally, the Milky Way knowing itself. And that knowledge, hard-won through centuries of effort and extending across cosmic scales, stands as one of humanity's greatest accomplishments. May we preserve it, extend it, and pass it forward to future generations who will continue the eternal quest to understand our place in the universe.